lead to inaccurate research results. Looking past the merely technical aspects, we must also invest time and effort in building sustainable user communities. These benefit users by providing an avenue for mutual technical support, but also academic software offers, as it strengthens the case for continued funding by evidencing user adoption. Lastly, given the global importance of climate research in particular, as well as the widespread benefits of scientific software to humanity in general, we should seek to improve access to high-performance computing infrastructure for all. This could be done, for example, by developing cloud-based access models with simplified user interfaces, establishing regional centers of excellence with local training components, and creating funding mechanisms specifically for computational infrastructure in climate-vulnerable regions. As most software for weather and climate science is developed by academic institutions and funded through grants, a good way to ensure that our recommendations are implemented is to make them a part of grant conditions. This works both ways. Funding should account for the additional costs of building more accessible software and maintaining it for longer periods. Practically speaking, funding needs to be allocated for dedicated teams of software engineers to support research teams in delivering user-friendly tools and high-quality documentation. This now concludes our presentation, and I would like to welcome any comments or questions.
Functional programming and so on.
Right, so if one sec, I'm hearing myself feeding back, and it's a little bit unsettling. If I just mute the laptop, there we go. So AI feeding into this. Obviously, at the moment, quality of code produced by LLM models is not great. You could develop sort of standardized interfaces for software and have correctness guarantees specified through type systems. Unfortunately, you still need a human expert to specify those in order to be able to guarantee some level of correctness. So ultimately, some sort of human will be required somewhere in the loop, even if AI tools are used to help generate code and accelerate development. Does that answer the question?
I guess no, it really does. Thank you. I'm really wondering about human peer review because we're all under quite heavy peer review stress, and if there's even more computational code coming out, it feels that there's a missing gap here in making it easy for humans to review and visualize scientific results. And I'm just wondering if that's one of the connective things that we need to spend more time engineering in order to make it easier to distinguish between what is LLM generated, what is the what is synthetic data, and then where do we focus our human attention to make sure that we get the best kind of bang for buck when it comes to the results of scientific computing.
That's interesting in a sense because it sort of mirrors the experience of actually using LLM agents to do coding. You're anybody that's tried it finds that they spend more time trying to review and correct what the LLM agent might produce. In a sense, that's similar to training an apprentice, for example. It's not quite the same because with a human apprentice, you have that human connection that you're teaching them new skills, and you can see them onboarding those skills over time. With LLMs, it's just repeated effort thrown into the void. Sometimes it pays off, sometimes it doesn't. For open source projects, accepting contributions, it gets a little bit more difficult because you might get a flurry of people contributing code, and that's asymmetrical in a sense, right? You might get a lot of quality contributions, or you might get a lot of junk coming through. I don't really have an answer as to how you could manage that situation appropriately. Ultimately, we'll still rely on human reputation, and it might just lengthen the cycles for contributors to gain trust in specific projects.
Okay. One very quick last question. Sorry, this this is
Go
not a
ahead.
question and more of a comment following on Anil's talk. But me and Zach down there, we've been working a lot on program synthesis with large language models, and well, something I had in mind was thinking about large language models as a form of program synthesis as a form of metaprogramming. So you sort of, well, I work a lot on metaprogramming, and there I deal with abstract syntax trees, and I was quite inspired by Agda and way back when epigram. We've got sheds or holes,
Yeah.
type holes in which we can perform generation, and so I've been building a language where you can have holes in like as in place of an AST subtree, where and in that hole you can insert a prompt, or you can have a prompt plus the old subtree, and you can say, okay, this subtree doesn't do what I want for this reason, and then what that does is it limits. Well, I have an interpreter that limits the LLM execution to only that subtree, and I think that could be quite a nice way of helping people who have some rough understanding of programming, but maybe don't know the nuts and bolts of how to implement a specific function to do that. It's sort of a generative way to call a particular library or write code that might be standard, but you might not know how to do, but you can see the overall structure. And I think this will help with verification as well, because right now when you ask Cursor or some LLM agent to perform a change, it changes a lot of different things in your program, and it's really hard to see semantically what the change is. But if you know that it should only change a very specific thing, and you know what specification you want for that component, then I think it becomes a lot easier to verify.
I agree in general with everything what you said. All the things that you've described are more akin to how fear improvers work, right? You have a type hole, and because of the type annotation on the hole, you can steer the LLM to generate something that is appropriate. Now, obviously, the more powerful of a type system that you have, the better that process can become. Obviously, with dependent types, you get a level of guarantee that is better than say less complicated type system. Now, there's other type systems as well. For example, if you look at multi-party session types that describe communication behavior rather than just a spatial type system, you can start to reason about sequences of actions or chains of functions that your application might execute.
Great, thank you.
Okay.
Thanks very much, Christian. I think we better stop there and move on to the next talk. But yeah, let's thank the speaker again.
Thank you. I appreciate it.
And please do ask questions to Christian online on the Discord. Hopefully, he can pick them up either now or later. So hopefully, we're okay for the.
Yep.
Okay, so we're going to go back to where we should have been before. So we'll have Jean-Michel Lord talking about programming opportunities for the Global Biodiversity Observation Network. Over to you, Jean-Michel, hopefully, this time. I think we're just trying to get it working, Jean-Michel. Can you see and hear? We can see you. Can you hear us? Okay. Oh. Okay, we're just trying to get it going.
But I don't see the room itself. Yeah, I can hear you.
Welcome to this presentation, the first of the Programming for the Planet 2025 edition. I'm Jean-Michel Law, will be speaking for GeoBond Network. And the topic of the presentation is Programming Opportunities for the Global Biodiversity Network. We will first dive quickly into the GeoBond network and the platform's purpose, but then the presentation will be focused on the IT aspects of Bond in a Box. GeoBond is an important network of practitioners that monitor biodiversity, and an independent one. It ranges from people cutting through the wilderness to others doing ecological modeling on supercomputers. This network has created essential biodiversity and essential service variables, as well as some adopted biodiversity indicators. To contrast these terms that we'll be using a bit in the presentation, the EBVs are by and for scientists. They assess the biodiversity status. Indicators on their end are by scientists as well, but for decision-making purpose. They track change towards an adopted target. Note that some ABVs are the basis for indicators. While ABVs are about standardization and comparison, indicators are about synthesis and interpretation. Then they flow into reporting to conventions that make the object of some political consensus. For example, the Kunming Biodiversity Framework has a monitoring framework that was adopted by countries in a historic multilateral agreement. A myriad of indicators were adopted, some of which we don't really know how to calculate. Others, only one lab in the world can do it. And for others, it's fairly simple. How is a country supposed to be able to report on all this? This is why we need to coordinate, not just locally, but globally. We're not speaking here of federating all the networks into one entity to rule them all. The countries want to own their reporting process. The GBIOS, Global Biodiversity Observation System, would rather be a network of networks, sharing knowledge, standards, and best practices, and helping each other out. It does not exist formally yet, but we strive for it and are inspired by the GCOS of the climate realm. I encourage you to read the Gonzalez paper for more details. This system needs a way to share analytics, and we provide a way to do it. A software to integrate biodiversity data and model that we call the Bone-in-a-Box pipeline engine. Bone-in-a-Box was an existing platform in which we added this calculation module to calculate essential biodiversity variables, indicators, all this based on a curated open source repository of community contributed analysis pipelines. So the GeoBond community in that case, but also larger. It feeds on local and global data sources. So if we look at this biodiversity data transformation chain, we're rather at the top of the pyramid, EBVs, indicators, reporting. The data and taking care of the reality and the data is done by some of them GeoBond members, but done by others. For example, take the Colombia example we have here. Colombia knows how to transfer their data into a specific indicator, whichever one. If they make the effort to generalize and contribute their expertise to Bone-in-a-Box in the form of a pipeline, other scientists that understand the theory or would take months to rewrite the workflow now have access to it. This same thing needs to be calculated in every country as per the convention. Another party could use this in Bone-in-a-Box with local adaptations if needed. It's a huge accelerator for the global biodiversity framework. And you can see the pipeline schematic on the right side. It's our next topic. The base unit of these pipelines are scripts. Here, you're familiar with scripts, I'm sure. It's our base unit, a single step that does one thing, transforming inputs into valuable outputs. And this cohesiveness empowers modularity within the pipelines. To integrate a script into Bone-in-a-Box, you simply need a description file and reading the inputs and outputs thing to the system. So it's fairly the same script that has been being used outside with modifications to ensure input validity and the sort. And the YML description file generates a form for the script that you can see on the right side. These scripts are assembled into pipelines, and this is what we call syntactic interoperability. The file is the only link between the steps. So a step could be an entire sub-pipeline or even run remotely. And this is why I say that interoperability is freedom within. As long as you are standard on the interfaces, in this case, the files, inside you can do whatever you want. Well, to the limits of scientific validity, of course. This is what a pipeline looks like in our UI editor, each of these boxes being backed by a description file and a script. And there are tabs to edit the metadata on the right. So every input that is not satisfied will end up in the same kind of form that you have seen previously for the scripts. And you can enter author, citation, metadata as well. The metadata and the missing input generate this form, and we can view the results in our visualizer that we call the results viewer. We have a more detailed view also that we can access all the intermediate results, logs, and code for full transparency, a bit less aesthetic, but for the sake of transparency, it's very important. And this leads me toward the founding principles of the pipeline engine, out of which transparency is one. So all the intermediate results must be visible, the source code, the references, nothing hidden. For the pipeline itself and for the run of the pipeline as well. The code and platform are open source. The scripts can be reused in many pipelines, and we enhance reproducibility since it's easy to rerun the pipeline with the same parameters or change the years and run for updated results. This is the founding principles of the pipeline engine. This is backed by a microservice infrastructure that can be ran on laptops or on servers. This is why it's important for data sovereignty that with the Docker Compose technology, we can easily run it on a server that would be internal to a country. They could be managing the access, and we're not responsible for handling their sensitive data. They are. So we're not being a data holder or a data provider, we can do it, but in event there is sensitive data, we really recommend the countries to handle it themselves. We can connect to any data sources that you can write a script for, and we will soon release a version where we can run jobs on an HPC over Slurm using Aptainer containers. So I stop here for questions one first time, then I'll dig into specific questions about IT science, and you'll have the chance to comment on those as well. All right, so I guess the video has been resumed. I can now ask my own questions. So feel free to do suggestions to give contacts, partners that could help. Some of these programming opportunities are things that are very remote, some are closer. And I'll walk you through them and the stakes. For example, the peer review. We have a peer review process, a bit like you have for papers, to make sure that the code meets the community standards, meets the documentation standards, and actually implements the scientific methods they claim to. So we want at least 3 reviewers. There's a formal form they have to fill. And once this is done, the pipeline is vetted. We change the label from in review to peer reviewed, and it can be used more safely. But we could freeze, for example, all the dependencies with Conda, but with multiple versions on the same package on the same platform, it would be heavy for an ordinary computer. And we want this to be able to run on ordinary computers and on servers with limited capacity, as well as big servers for heavy calculations. So we don't want to freeze all the dependencies. But if the dependencies change, what happens? Do we need to re-review to make sure it didn't break anything? Or if we find a bug in the pipeline and we resolve the bug in the pipeline, do we re-review again? We might do static tests. Okay, these inputs should give these outputs. But they might miss a particular situation, or also, we can only perform so many static tests because these are intensive computations. So we don't want to retest so many different scenarios every time there's a small change. So my question here is, can we detect if the change either in the to resolve a bug or to a change in dependencies has a major impact on the execution flow? Can we have a hint about what should be retested and what does not need to be retested? Easier if it's a bug that was resolved, harder if it's a dependency change. I could imagine something like this function graph here where the percentage of modification for each function could be written in line on the script, or maybe conditions of the change. Well, this will be affected only if this parameter is true, or a visualization of the call tree, and then we see the differences and can try to backtrack to the main script and see if there's any effect. That's a bit heavier. Of course, the second proposition here is really interesting because it's the less work to do, but it's probably the harder to program. So I'm wondering if something exists already or is near to exist that could perform these tasks. Stop here for your input. The next one is the data visualization. So the inputs and the outputs are as varied as you can imagine. We get all sorts of inputs, geospatial occurrence data, and shapes, and we output so many things as well. And we get along well with a few standard types, but there are questions. Could I manually clean occurrences live between two steps? Do you support interactive graphs as outputs or this specific data format? So my question here is, could we plug in data visualization decided by the pipeline contributor, but for which we are not the maintainers? For example, could we use WebAssembly to spawn a QGIS for data addition and then take the results and continue the pipeline? But in a way where we don't have to do specific things in our backend and our front end for each of these platforms. Maybe there's a library or somewhere that allows to plug these things more easily. So this is where I will listen to your feedback. The next topic is the chains of trust. This is a forward-looking one. Currently, bounded box instances don't communicate with each other, so this is for the future. Take an endangered species, for example. At the occurrence level on the left side, there is a risk of poaching if the data leaks. Once modeled, it's a lot less sensitive, but could still be considered so by local authorities. Someone could look at the map, oh, there could be this species in that region. But once aggregated into indicators, there is no risk for the species. How much different species are there in a specific location in that example doesn't tell you if you could go poaching for one specific species. So if we have data flow from the data source through bounded box nodes to an aggregated version to the CBD, well, there are some parts that are sensitive. What technologies should be used to build these chains of trust, ensuring that permission level required to access the result lives in the metadata, and if possible, evolves with the level of aggregation. For example, we don't want to block the whole bounded box instance, but maybe only viewing some products based on the level of sensitivity of the data. And again, I'm listening to your suggestions here. finally, the dynamic data flow. Currently, pipelines explicitly support some data sources and uploading some specific user data for some parameters. But in the spirit of maintaining the integrity of the peer-reviewed pipelines, but allowing to integrate multiple, possibly unforeseen data sources, it would help to accept only a standard input in the peer-reviewed core and compose a pipeline by prepending an adaptation layer that converts data into the suitable format for the pipeline. We came across semantic modeling, which would be very elegant to solve this for major global sources, but the learning curve is steep and we cannot afford to teach the syntax to everyone who wants to use it for local data. So then we could also write converters manually and dynamically assemble them. This surely has been done already somewhere, so maybe we could reuse it. So I'm listening here to your suggestions again. Well, thank you very much for listening in. Feel free to contact me at web@geobond.org or to leave your address to Anil, who's in the room. And I'll be delighted to respond to your questions and have a good Programming for the Planet conference. Thank you.
So I have two questions. First is, does one in a box is more like a data space for like biodiversity data? And if that is the case, why don't we use the existing data space and then just do things on top of it? Because I'm pretty sure there are like a bunch of PL techniques that's been using on data space. There's a line of research in that area. And the second is a bit more technical. That is, say we have two different data sources and of data coming from two different temporal or spatial resolutions. How the mismatch or is in general, how's the mismatch in data is detected? So yeah, these are the two questions.
Hi, do you hear me correctly? Okay. From my own voice, so I'll mute myself while I speak.
Yes.
So the data space. So Box is not data provider. It's a way to transform the data from its original source, whether it's in GBIF or in some spatial temporal assets catalog, into a derived product. So it's really a place where we transform um, the the data into a product that is useful for the biologist or for the decision makers. So it's more about transforming the data. And when we speak about fair data, it's a lot in the words these days. Fair data for all this biology data, but we also think of fair processing. Can you find easily how to do the processing? Is it accessible to ordinary biologist? Just these two first questions is probably no in a lot of cases, unfortunately. So these are the sort of things we're trying to address, and same for all the rest of the letters. And then for the data sources, well, the example you used was about spatial temporal resolutions. In this case, we just used the stack catalog technology with cloud optimized geotiffs, and we query them using GDAL cubes. And with GDAL cubes, you can just on server and download just the right part of the file that you need. This is more on the expertise of some of the people writing the scripts than my own expertise. But that's what they use for harmonizing geospatial data. But when we speak of taxonomy, it becomes much more difficult. There are ways to do that also, but it's not Bon in a box providing the solutions. It's people using provided solutions, code scripts in Bon in a box.
Great. Last question, anyone?
Yeah,
Thank you for the question, by the way.
you talked a bit about kind of potentially change propagation or some kind of detection that, you know, a data source might have changed, or perhaps there's a new revision to a data set, and then kind of propagating that through your pipeline. Is that something you're planning to do, or is something you've already got some kind of infrastructure for?
So just to make sure I understand the question correctly, you mean something that would live update whenever changes? Is that right?
But not specifically live update, but maybe I misunderstood what you mentioned on the slide, but I think you were talking about detecting when inputs have changed and working out which parts of the pipeline might have been invalidated by that change.
Okay, yeah, I was really speaking there of the code behind it. So a problem that is already arising is that we have our first pipeline that went through peer review, and if the dependencies change, the new results might be incorrect just because of the package updates. And it's really here not the source data that has changed. Again, Bon in a box is more about harmonizing and being fair on the way we transform the data. So in order for this to be reproducible, the same peer-reviewed pipeline has to behave exactly the same way. Of course, we do a dependency dump just to know which dependencies are actually there when the pipeline is peer-reviewed. But then, and we can always revert to exactly these dependencies to be sure. But in that spirit, it's really the dependencies that change, or a bug that was resolved that would do a change in the processing, and this is what detect in order not to either retest the whole thing all the time, which is basically like launching tasks on HPC because you're testing 3,000 species for the whole Canada. Well, that's not convenient. Or missing these edge cases. So having an idea what in the code, a hint on what we should retest would really help us.
Yeah, I think I misunderstood what you were talking about. Thank you.
Thank you.
All right, let's thank Michel again. Yes, thank you for joining very late there. Okay, so we're a bit behind because of the technical difficulties, but the last talk is pre-recorded. That's coming, I believe, has been recorded by Prerak Shah, who's going to be talking about the work on patch, precision action towards climate and health. This is going to give us some kind of broad view of applications going on in this space. So hopefully we can run the talk.
Hi everyone, good morning. I'm Prerak. I represent an organization called Catalyst Management Services from Bangalore, India. It's part of the larger Catalyst Social Enterprise platform, which hosts different organizations with focus areas across, let's say, public health, livelihoods, climate, governance, and likewise. We are based out of Bangalore in India and have been working in the social impact space for last about 30 years. And our footprint spans across multiple countries, across 25 different countries in Southeast Asia, then some of work in Africa as well. So today I'm going to talk about the precision analytics in action towards climate and health. In the short form, it's called PATCH. It's a framework and early warning system intelligence tool that has been developed to respond to various climate and health mediated risks that are emerging across the world now, and specifically in the lower and middle income countries. And this initiative has been started by Swasti, a public health organization, which has been working in this space for about 20 years and anchored by them across different countries with relevant partners as well on the ground. So, I mean, I'll just go into the details of what we aim to do. I mean, we all of us are aware of what we are trying to solve here, right? So basically, idea is that okay, climate change is affecting different health system. We are aware of that. Okay, every year on year, the temperature is changing, the floods, the landslides, the droughts, all of them have become very uneven as well, right? And these are unpredictable, specifically. And most of the brunt that is faced by all these events are towards the vulnerable communities who do not have access to the basic necessities and the resources, right? So our work at Swasti has been largely to improve well-being of vulnerable communities and add about 100 million healthy days by 2030. That is what we are aiming and working towards. So a lot of our efforts from Precision Health platform over last 4 to 5 years has been around setting up the systems, converging with the government departments, and scaling it across the states to help governments and the relevant departments and the civil society organized to operate on the ground where they can work closely with the vulnerable communities to improve their livelihoods, right? So this is just a context where all of us are aware that, okay, climate change is affecting everyone, and this is going to be there for next decade or so. And how do we help vulnerable communities protect themselves and react or respond to the different events that are happening in much more effective manner? But for vulnerable communities or any institution to even react to that, they should be aware, okay, there is an upcoming event or there is a distress event that is going to happen. So that is what the precision health is all about. I mean, this is just a more broader scenario on all of us are aware, right? All the climate events like flood, heat, drought, the risks are massive and they are increasing as well. Specifically in India, where we are based out of, we have seen that across different states, things have changed drastically. Let's say in Northeast, in a state like Meghalaya, where dengue and malaria and all used to be very unknown term, now it has become so prevalent that now government is addressing that in a systematic manner, right? Similarly, in Tamil Nadu, where they used to have, let's say, monsoon rains about early, I think October, November, and then later in the late monsoon rains also around January, right? But now there is a reversal in the pattern itself. Probably instead of lack of rain, now there is a floods that are coming in the state. Likewise, each of the state in India faces different challenges, and especially when where the vegetation is higher, they also face uh, other challenges with, let's say, zoonotic diseases, veterinary diseases, and all of that, right? Besides that, we also see that there is a lot of antimicrobial resistance that is increasing across the country. Not by the study, but in a general consensus across the practitioners is also that certain antibiotics that used to be more effective are not that effective now. Let's say, right? So there could be underlying potential antimicrobial resistance that could be developed, and there are accepted papers as well, right? So what Patch basically aims to do, Patch is an architecture or a, I would say, convergence platform where we sort of bring different data sets together to help government or likewise any system actors who is working towards vulnerable community on improving their well-being in getting the right intelligence via, let's say, bringing different data sources together, via, let's say, convening different stakeholder workshops, via, let's say, having community voices being heard to the government, all of that different tools. I'll talk about those tools in a bit. But why these tools and convergence platform is more important, because it's not only about bringing data system or creating an architecture, but also working with the different government systems and relevant entities to define the problem itself, right? Probably the problem that we might see in Meghalaya may not be the same in, let's say, Tamil Nadu state of India. Likewise, whatever we are seeing in Gujarat may not be applicable in, let's say, even Bihar. How do we even work with the government or local partners to help and understand what are the key challenging area that they are facing, especially from the public and climate point of view? then bringing right data sets and the architecture together to address that in a timely manner so the early warning system can be set up and operationalized, right? While we do that also, we also co-create the same system with the users who are going to use it. So keeping human in the loop and having a user-centric design is the core principles for us, where we ensure that whatever we are developing is with the support of those local partners and governments, right? In the past of about 4 or 5 years across, let's say, COVID, then different events that has happened across the country, we have had different tools working on this together, right? So we started with, let's say, wastewater surveillance, where which is based on the water-based epidemiology. Then we expanded that to, let's say, GIS-based vulnerability mappings. Then we also have an in-house tool for event-based surveillance, which sort of scrapes all media articles to give an early warning system where likely spread is going to be. I'll talk about some of this in the detail as well. But what all of this tool helps us is a hyper-local solutions that basically helps in identifying where the distress or the event is likely to happen, and also give that particular information to the local partners, since we are also anchoring a collaborative for about 400 organizations are spread across the country, where we can disseminate this information to those local partners and the government systems as well, saying that, okay, there is a distress that is likely to happen. So how do we act on it and provide relevant support that is required for it, right? So we also have a risk communication entire material, which also helps in disseminating some of this scientific and technical insights to a frontline worker, which they are able to consume in a more effective manner, right? So a lot of this work is happening as part of the precision health platform. So the way it happens is, let's say, when we bring it all different data sets together, either via public sector data, private sector data, civil society data, even sometimes talking to the community, then publicly available information either via social media or newspaper, all of that we bring together. Now, when I say bring together, there is an underlying architecture which exists where all the state departments has a certain, I would say, uniform infrastructure available. There'll be certainly customization which is relevant for each of the context. I'll speak about some challenges also in that process that we have had. But in the last couple of years, we have been able to integrate a lot of, let's say, weather-related data coming from Indian Meteorological Department, scraping some of the publicly available information across the country, right? And bringing together in an architecture. So whenever you move to the next state to identify different problems and support different stakeholders, we are able to do that more quickly and help with the uh, help with the solution in the right time, right? So most of the our solutions and the platform audience is typically the governments and the local communities or the civil society organizations who sort of consume this information, right? And again, since this information goes via let's say either a playbook or even a simple text message. Sometimes it's via a handbook that goes to the frontline workers in a print version. Sometimes it could be a chat bot. All of that is available, right? Then what it helps is that, okay, it provides a hyper-local solution which helps the frontline worker or a civil society organizations to work with the communities to protect themselves from any of the climate-mediated health risks that are emerging in the particular geography. Now, why it is innovative in a way? Because over the past years, we have seen that bringing all these data sets together and also working with the community is always challenging. So we are able to do that because of our expertise across working with almost 1,000 plus community institutions across the country, working with almost 10 plus different state governments plus national governments in India and likewise in Philippines as well. And also uh, having the cutting edge technologies like GIS, AI, and also bringing different domain expertise that we have across the Catalyst platform, right? It allow us to basically bring in all the different data sets together along with the relevant domain expertise, which helps in providing the right solution at the local, hyper-local level, and also enabling the frontline workers to act on the ground in a timely manner so they can protect the vulnerable communities. Now I'll go into a bit of technical details about each of these tools. I think these are the 5, 6 different tools that we have been using in the past, and it's not a laundry list of tools. It also evolves as and when the different use cases are being developed and defined as well. So what it does is, let's say, water-based epidemiology, where we had used across 5 different cities in during the COVID time. Then we sort of expanded it to other diseases like influenza, hepatitis, and all of that as well. So what it allowed us to do is like predict the COVID a week in advance, right? Because there is a science which tells that you share the virus of COVID much before it can be clinically diagnosed in the hospitals, right? And specifically, the core principle that we wanted to follow is also to cover the vulnerable communities who typically are not covered under a well-established infrastructure, right? Because we come from the public health equity point of view. So what it allows us is that when we sample the wastewater from the open drains, right, typically which are not part of the sewage treatment network, which is established by the municipal governments typically. So, but when you sample from the open drain, it also represents the community which are staying nearby and does not have access to well-established, let's say, sanitation infrastructure. So, because of this, and when we mapped out all the sites that we are doing about, let's say, almost 50 plus sites for over 2 years when we were doing regularly, we realized that we were able to cover almost 86 to 90% of the population across the city. And again, Bangalore is a city of almost 15 million population, right? And when I talk about these 5 cities, almost we are catering to 25 million population, right? But based on the GIS and using certain technologies where we are able to map how would water flow from one wastewater to another wastewater based on the topography, based on the elevation, based on the slope, all of that, right? And also using the, let's say, neighborhoods typology mapping where we are able to use, let's say, vegetation, street network, heights of the buildings, density of the population, all of that, and understand which are the most vulnerable population for specific diseases like which are, let's say, communicable in nature, like COVID or hepatitis and whatnot, right? Different, I would say, communicable diseases could be identified, and the same method can be applied wherever those are identified in the wastewater. And we were doing something with event-based surveillance where this is again pre-ChatGPT era where we are scraping all the internet media articles across the country, not only in English but all local languages as well, where we are used to filter and summarize and put it in a certain way which is consumable in nature for the relevant stakeholders. Right? Once these are available, instead of a human spending almost, let's say, a week going through about 100 articles, now this makes the entire process smoother within an hour or so, right? So now you have timely information, probably more advanced in nature as well. So let's say by the time you summarize and have all the information, the disease would have spread. But now when you know that, okay, there is a disease that is going to be likely coming in, let's say, Bangalore. So it's also likely to be affecting, let's say, nearby cities. Just giving an example like that, right? So how do you act on time so you can work with the vulnerable communities in advance? Likewise, we are using a lot of GIS data. Again, this is something I won't go into the details of technical methodology, but what it does is that using relevant 6-7 indicators or factors which can influence floods in a particular geography, we are able to identify which are more likely to be flood prone at the village level. Now we are using quite a bit of indicators like digital elevation map, distance from water body, topographical wetness index and all. And then there was a model which was well accepted by the researchers in the country like say, Nepal, Bhutan and all of that. So we are using similar model like analytical hierarchical process where having a contribution from the experts where they define which is more likely to be affecting flood, right? Likewise, this is just an example of a flood, but this also applies to different events like even sometimes drought, sometimes climate and temperature related distress that are going to happen. So likewise, bringing all this data architecture in a way where there is a timely, let's say, communication which is available to the government or local partners, either via dashboard, reports, or systematic alerts, but also bringing the feedback loop from the ground workers on saying that, okay, this is how the data and information is right? Look, because we also have a lot of community base across the country. So we get that feedback and are able to improve over time. Now, this is broad data architecture that we have in place. I'm just going to talk about where it is operating right now. I mean, we are operating across 3 different states of India, Meghalaya, Andhra Pradesh, and Tamil Nadu, and one province in the Philippines as well, where, again, the use cases are defined along with the government and the local partners who are working there because they know the geography best right now, correct? And to effectively use their expertise and also bring our expertise, we sort of try to marry both together and also then work with them to develop the solution and disseminate the solution in an entire chain of the action, right? So in Meghalaya, we are working in the One Health domain where at the intersection of animal health, human health, and environment. Then in Andhra Pradesh, we are largely focusing on how heat is affecting different health-related interventions, specifically on RCS and typhoid. Then in Tamil Nadu, the focus is on scrub typhus and antimicrobial resistance. And likewise in Tobacco City, it was more broad at the governance level on how do you improve the health service delivery, right? Now, all of that has a different use cases, and entire architecture uh, uses basically different components from that. Now, let's say a lot of modeling that we do, I'll just give you an example how we also approach. Let's say I'm just giving a use cases from Tamil Nadu where we are trying to predict the scrub types across different places. So how do you use, let's say, health data along with environmental data, which is available publicly via satellite, the geography data about land use, the agroclimatic zone, vegetation covers, and likewise, right? So bringing all of this together allows us to work with the system to understand, okay, where is it likely to be happening, right? But since this is a technical conference and the audience as well, I'll put out certain of the challenges that we have been facing over last few years, right? Specifically, access to the hyperlocal GIS data. I think some of the times we are able to access some data set at the, let's say, probably 1 by 1 kilometer level, right? Not beyond that. Sometimes even 10 by 10 kilometer level. This depends on the satellites and the type of data available. So I would love to hear about how do we access more hyperlocal data sets so we can provide much better insights to the communities and also help them protect themselves from all the climatic risks that they are facing. Then creating an architecture. So a lot of time while we have the architecture in place from the design point of view, interoperability becomes very crucial, right? So some of the data sets which are available across different states may not be talking the same language across, right? So how do you make them interoperable so that you have a larger and larger data set available when you replicate to more states, and also use that as a training and test data set so you have a much more better confidence in the type of models that we are developing. And there are certainly context-specific challenges. So let's say when we are trying to do flood mapping for the state of Meghalaya, we realized that the flood mapping, the way we were imagining, will not work there because these are the hilly regions where landslide is very common. The road networks are very differently designed and all, right? So how do you deal with specific challenges like context, like let's say northeast of India, where the entire topography is very different, right? Likewise, in Tamil Nadu, since they are closer to the coast, they also face different challenges around rainfall. Suddenly, the rain will change or delay or come early by a couple of days, right? There will be sudden floods. So, how do you get some of these early warnings in advance? Is something I would love to hear based on everyone's experience there as well. But yeah, these are some of the challenges that we have been facing, and I'll stop it at there. But happy to answer any question and sort of address anything that you might have on the platform. Yeah. Thank you so much.
with this? All right, great. Cool. So actually, I'm going with Anil's suggestion. So he suggested that, so we have two papers. I'm going to give a brief introduction to both of them in this talk. And then in the next session, I'll give more of a demo of various things. To give a bit more context, in all of our work, we're very driven by understanding what problems or what questions our community is really trying to answer. So that kind of informs what eventually computational problems are we ending up solving. So we do a lot of field visits in rural areas, in different parts, and just to give some idea, right? These are examples of farm ponds. This one is what's called an unlined farm pond, which essentially collects rainwater, and then all the farm fields close by, they benefit by way of improved soil moisture and so on. But this one, what you see is a lined farm pond, where the use is very, very different. Here you actually pump water from the ground, yeah? And you store the water and then use it for irrigation. So the kind of questions when it comes to an NGO trying to do some planning, right? This one is basically trapping surface water and sort of preventing runoff going further down. But this one results more in groundwater depletion, right? So how many such kind of structures can a landscape support? And then likewise for a farmer, yeah? That if I were to do a farm pond, where currently I'm doing some cropping, so I'm going to take away that land and put a farm pond over here, how will it actually benefit me? How many weeks do I think this farm pond will hold water? Yeah, those are kind of micro questions. Likewise, some other things where there's a lot of room for informed scientific planning to start happening, fields in downstream areas where the upstream areas are forested, those fields get a lot of very high nutrient runoff because this water coming down from the forest that's rich in soil organic carbon and everything. But many of these traditional systems have sort of gotten sidelined. People rely more on synthetic fertilizers than kind of natural runoff and so on. So, you know, those are the kind of things that there's a lot of scope for improvement in, and in some ways, you know, going back to traditional systems that were out there. Likewise, you know, questions like if I want to do more commercial cropping, right? How much area can I bring under sugarcane plantation, right? Or not me, right? But for the village as a collective to answer, right? How much, you know, area under commercial cropping should we actually have? So that's really the kind of things we're trying to answer. And there's like a rough categorization, right? That when it comes to computationally solving some of these, then what are some of these questions, right? So a lot of the work currently that we see happening around us sort of revolves around pixel-based things, where largely you essentially have a mashup of different raster layers, where you want to sort of combine one raster, take its output, put another layer on top of it, and sort of like identify, right, which forest patches have seen some kind of degradation. And those areas become important for restoration planning. Yeah. Some more, in fact, the GeoBond talk was talking about building indicators, right? So this is slightly more complex, where you start using some raster layers and sort of figure out, okay, which particular areas or hydrological units are more, let's say, drought prone than others. And in those areas, is there also a lack of surface water availability in those areas and so on. So these, again, are helpful for planning purposes, that which particular areas can benefit from you know, different types of interventions, yeah? But what we also need is a lot of coupling with hydrological models. And here again, there are different approaches, right? So in this pixel-based category, what I've put down is what civil engineers do a lot of basically finite element simulations to understand how groundwater flow or surface water flow is propagating. So again, these kind of things can be important, right? That if you were to do a particular plan, right, come up with some new check dams or gully plugs, right, what particular area will really benefit? And then more complex stuff, right? So some of the things we were, in fact, just talking about over lunch, that can you divide a particular landscape into different units and say that, well, if I were to do afforestation over here and come up with new water bodies in some areas, right, how would it impact cropping? So this really, right, you're representing the landscape in terms of units and figuring out what are the connections, what's the nesting of these units, and then you can do all sorts of different ML models on top of it. So the two papers that I'm going to talk about, right? One is about figuring out that in these kind of use cases where you're talking a lot about raster layers and coming up with indicators on different spatial units and everything, there's a big problem of data and algorithm management. Actually, what the Geobond talk was really talking about. And in this part, there's a big problem of scaling, right? That the more micro you go, how do you really do faster computations and right at this very high resolution? So coming up with this first part, right? This is an example of a data flow graph in the setup that we're trying to build called the core stack. So basically, there's some raw data that you start with on which you apply some algorithm that produces some other output and so on. Yeah. Now the problem is that if let's say we were to update an ML model somewhere, right? We have now new ground truth. We update the model. Then you want to recompute all the stuff downstream. But again, maybe you don't want to recompute everything, but you want to have some sort of determinants that if the outputs at some point are not differing a lot from the previous version, then maybe don't compute. Yeah. But also figuring out version management, right? That for any particular data set that you've produced over here, what's the lineage? What version of the algorithm actually ended up producing it? Yeah. So you want to maintain all of that information in some way. One of the main standards for data sets is the STAC standard, spatiotemporal asset catalog. Yeah. So again, it's very straightforward. Basically, you talk about, right, what's the resolution, what's the projection system, and a couple of other things, right? But there is really no scope for maintaining lineage information. The only one field which is kind of there is a derive from field. But in fact, we failed to find even one stack standard where this was populated. So what we're proposing is just something very, very simple. Basically, we're saying that let's think in terms of a representation of a DAG. So this DAG has some parameters on which you want to execute that whole DAG, right? Parameters could be like the area of interest or some years on which you want to run that whole DAG. Now, what this DAG does is that is basically a sequence of algorithms. So you know what algorithms and input data sets are needed. There's a description of the algorithm that what inputs is it going to use. And there are versions of the algorithm implementation. So you can keep, what you want is that you keep updating the algorithm without sort of fundamentally changing what it's meant to do and without changing the input and output formats and sets, but you want to update different versions of it, yeah? And then likewise, these basically then produce ultimately different data set instances. And this is basically what's this you want to put into a stack. This is basically your stack item actually. But behind the stack item, you want to maintain this whole machinery, yeah? So, so this is what we've done. We've basically come up with a simple YAML representation of the DAG. And we've also done a reference implementation in Airflow. Apache Airflow is an open source workflow orchestrator where you can basically give it a DAG and then it executes the DAG, right? And it takes care of the sequencing of operations and dependencies. So basically what this does is that it takes the YAML configuration and then Airflow internally requires the output, the DAG to be coded in a particular format. So there's a converter which basically converts it. And then this Airflow can then trigger different kinds of computes. So one thing that we've implemented is basically that the algorithm instance is described in terms of Docker parameters, right? So what's the Docker image and mount points and everything, and then it executes that. Similarly, there's another with API-based things that I can invoke an API. This API in turn, there could be something which goes to Earth Engine, computes stuff, and brings it back. And then all of this is maintained in a database. Yeah. So, and on this, we've also implemented a couple of simple things like full exec is, it executes the entire DAG on the particular set of inputs. Algorithm update is where some particular algorithm in the DAG is updated, and then everything downstream of it gets recomputed. Similarly, dataset update, DAG augment, that you can augment the DAG with more nodes and edges, and internally we figure out, right, which ones need recomputation, and we recompute. Then some more things that will be very interesting, right? We're trying to work on these things, right? Define how far should this recomputation progress, right? Based on whether the data sets, the outputs are sort of differing more by a particular delta, or what the Geobond talk was also talking about, right? If the algorithm is, through static analysis, if you're able to figure out, right, if this is very different, then maybe you then trigger a recompute. So that's the stack work, and I'll change gears and also briefly introduce, right, the other kind of problems that we're trying to solve with doing faster algorithms for these kind of hydrology simulations. Yeah. So here, the main purpose really is that there are these hydrology simulators like, sorry, what's the major one? It'll come back to me. But they don't sort of operate on very fine timescales like ours. Rather, it's daily kind of temporal updates that they do. Or the spatial units that they consider are quite large, 1 km square or larger, and not like a pixel level 30-meter sort of a resolution. So and largely they're all CPU based. So that's really where there's an opportunity to recode many of these algorithms. So one of the things that we wanted to do is basically simulate runoff. That when it rains in a landscape, how does the water flow? And there are different, the civil engineering folks have all sorts of numerical methods of figuring out that if it rains and based on the past rainfall, how much water will infiltrate, how much will run off, and they take the soil type and all sorts of things into account. And based on that, you want to recompute. Yeah. So, so in a given landscape where there are this is represented through a digital elevation model that the elevation of each pixel. These are 30-meter pixels which are out there. So on this, now when it comes to this runoff computation, you of course first have to compute the flow direction. And here, one of the simple algorithms basically just says that the water will flow down the path of steepest descent. So this is now a straightforward operation which is easy to parallelize, basically a short pixel operation, right? Because on each pixel, you're basically seeing its neighbors, yeah, and seeing that for this pixel, therefore, what is the direction of steepest descent? And it's similar to a convolution operation, right? Which is easy now to parallelize on a GPU, yeah? The harder part happens that you then have to run an iteration that where will this water flow eventually, yeah? So this is now an algorithm called flow accumulation, but that is sort of unbounded, right? Because it can keep propagating up to sort of the length of the path over which this propagation will keep flowing. So this is a long pixel operation, and that is harder to parallelize. So this is basically just a trick that we came up with, which I'll talk about of how we do that, yeah? Then there's more complex stuff that you do, that once you have the flow accumulation, you define a particular threshold, and anything above the threshold are what are called drainage lines. So basically what happens is that these drainage lines are where more flow is accumulating. So once you threshold, you actually come up with the path along which the water will travel, yeah? And then there's cool stuff that happens after that, right? You find out which of these are head streams. They're called stream order 1, and then 2 streams of stream order 1 will combine together to produce a higher order stream, and eventually you end up in a river, and the river goes into the ocean and so on, right? There's other things that are also done, which is used for the hydrology folks talk in terms of hydrology units of watersheds and micro watersheds. So here again, they basically take points on these drainage lines and they figure out that on this point, what is the catchment that is flowing into that point? So this becomes a micro watershed. And so again, these are basically different versions of long pixel operations, and you eventually break up a particular landscape into smaller units. And these units are easy for analysis because basically what happens is that whatever rain is kind of falling in one unit is sort of constrained in that. Yeah, there's one outlet point from that. And then it is on this that you then do your runoff accumulation, that basically you look at your rainfall, what is the land use, the soil group and the slope, and this is and the rainfall, and it's based on this that there's a lot of numerical models which then give you what is the per pixel runoff expected, and which then has to propagate along the flow direction. And eventually you want to come up with these kind of what are called hydrographs, that along some network of points on which the major water will flow, how much meter cube per second of water is going to flow. Yeah, so this is basically then this becomes important for flood modeling and all of that. So the reason to do it at a microscopic scale is kind of, right, like I was saying, to answer those kind of questions, that even if on these small order streams, if somebody were to do a check dam, then the farmers are interested to know that if a check dam were to be done here, will my fields not get waterlogged? Yeah, or if a water body were to be rejuvenated, then what's going to happen? Yeah. So now on GDAL, many of these are CPU based, so they take time. Platforms like Google Earth Engine don't support long pixel operations, and the biggest, this you might even be able to compute statically because this is not changing, but with runoff, if you want to do it on a hourly basis, right, then that becomes a killer. So that's where it's a simple trick that we did. Basically what we do is that on a particular, right, for each of these pixels, we figure out what is the velocity on which, with which water will flow, and then in a given time step, you can sort of know that, okay, this pixel in 1 second will go where? Yeah, the water that is generated as runoff from this pixel, where will it go? And we use this to build a jump matrix, basically. Yeah. So what then happens is that this long pixel operation essentially becomes a lookup operation. Yeah, that this is just a row major indexing of the pixels. So what you can then determine is that the pixel over here, if some runoff is generated at that pixel, which other downstream pixel will it go to in 3 hours? Yeah. So this basically simplifies the problem, right? That now you don't have to do the whole iterative computation, right? But now it's basically just a lookup operation, and which you can then do on a quick basis. Yeah. So this is just, right, the area that I was showing is this particular area, and this is the much larger, what's called the lower Ganga basin. So what we're actually able to do now is that on this large area, 250,000 square kilometers, this is rainfall, and we're able to do the simulation on 30 meter pixels. Yeah. So this helps in that. There's a lot of other stuff which is also happening in the broader ecosystem around not just using these process models, but think about machine learning methods to do that. Yeah, so I'll stop here and yeah, take questions. Yeah.
Questions? Questions? If you have questions, please come over to the mic.
Thank you very much, Adi. That was great. I had a question about the adding the DAGs for the having the algorithms within the stack. I was wondering if there was ways to add things for reproducibility. So whether you kind of have these things that allow you to say, you know, this data has changed, so you can rerun stuff. And I was wondering if there could be some automated kind of tooling to decide that this data has changed because a hash has changed or this algorithm has changed because this hash has changed. This Docker image is no longer the same Docker image, it's been pushed and it's a new one, and these sorts of things to try and bring some reproducibility into that as well.
Yeah, no, I mean, very, very useful, you know, this is just very, very early work. We've still in the process of building, but, you know, there's a lot of scope to build further tools and everything on top of that. Yeah.
Iterating on this technology will allow for things like flood prediction, or will that require
No, I mean, that's something we want to investigate. Largely for things like flood prediction, mostly using these kind of process models, lower resolution simulations have been done. And then they're kind of compared with machine learning driven methods that are able to learn many of these features. So it'll be interesting that now that we can do higher resolution stuff, are these process-based models able to do better? So that's really one of the next steps in this.
Excellent. Let's thank the speaker again.
Thanks.
All right. So the next talk will be given by Rolly Pereira on authoring tools for transparent climate reporting.
Yeah, my name is Rolly Pereira. I work at the Institute of Computing for Climate Science. I work with Dominic. Oh, that's the end of my talk, not the beginning of my talk. If only. Okay, so I'm going to mention some collaborators as I go forward, but I just want to shout out these three people in particular because they've done a lot of the implementation work over the last few months and years, and some of the organizations that have funded and supported this work. So when we communicate climate science, we rely on charts, text, and other summaries. This paints a high-level picture, if we're lucky, but the relationship to the evidence base is quite unclear. It's often not clear what data I'm looking at, how these conclusions were reached, and so on. And if I want to dig further into this myself, then I have a very difficult problem. The data availability is going to be very sparse, and what to actually do with the data is going to be very hard as well. And there may be some text that helps me understand what I'm looking at, but that text is going to have that same kind of problem as well. There's going to be all kinds of science and numbers scattered throughout the text, but it's going to be unclear where these things actually come from. So one way to frame this problem is to think of it as a disconnect between the world in which we do science and the world in which we communicate science. And computational notebooks like MIST and Jupyter are a kind of step towards bringing these two worlds together, but they have quite a few shortcomings. The cells still execute as black boxes. They have a very flat structure, and the decomposition of the pipeline or the workflow into cells is determined by the author rather than by the reader. Now, I'm not proposing in this research to address all these issues with notebooks. Our contribution in this space is a language called Fluid, which we describe as a transparent programming language. So what I mean by that is a language that tracks how data flows through the computation and then is able to automatically enrich outputs with queries that allow a reader to explore the provenance of what they're looking at. And these are a couple of papers that we've written on the kind of theory, if you like, that underpins this language. So what I'm going to try and accomplish in this talk today is just present a simple example that we've started working on recently of applying this to a real policy document. So normally I cherry pick my examples to show our language working at its best. So this is very much not in that space. So I'm going to highlight some of the difficulties to do with our implementation, but also the kind of data quality issues that come up in reproducing this kind of thing, and mention some of the ways in which we're going to address some of these challenges going forward. So what we've been looking at is this independent assessment of the National Adaptation Programme, NAP3. So this was produced by the Climate Change Committee. So this is an independent advisory body that advises the UK government on resilience. So in other words, how well the UK is able to kind of be resilient in the face of climate change. So, and this is a project with a couple of collaborators at Bristol. It's very early stages, and this will probably feed into some of the other projects that I'm going to talk about at the moment, but so far it's a kind of standalone activity. So let me show you what this looks like when we try to sort of reproduce this in Fluid. So, okay, so this climate change risk assessment, CCRA3, identified 61 risks and opportunities for the UK relating to climate change. This report then evaluates this NAP3 program, which has a bunch of commitments for activities and actions rather that the government's going to take. And it evaluates those commitments to see how well they address the risks and opportunities that were identified in the CCRA report. So what we have here is a couple of figures with a caveat that we've reproduced from the report. So the figure on the left is figure 1 in the report, slightly altered, and the figure on the right is a figure from the Excel spreadsheet containing the data for the report. So when we implement this in Fluid, what we get is a kind of transparent version of these figures. So what that means is we can access a view of the underlying data on the left, and then we can interact with parts of the output and get a view of the inputs that are relevant to that particular output selection. So as I move around in the output, I can see which parts of the data that I'm looking at. So if you look on the left, you'll see that these data sets are actually quite a bit larger than what we're looking at here. So there's about 5,000 elements in the data here. And we're just looking at 5 rows in this case and 2 columns of a larger data set. Now, if I click on this purple segment here, then I'll see that some of those purple segments on the left have been highlighted as well. So the chart on the left, sorry, I should have explained. The chart on the right is showing actions from the original CCRA assessment organized by governmental department. The chart on the left is organizing those same actions by chapter. So this highlights one of the data quality issues that I mentioned earlier, which is that this data set doesn't actually have the names of the chapters in the data set. So in the Excel spreadsheet where they computed these figures, they just used hard-coded ranges for the cells, essentially. And because the rows were sorted by chapter, that worked reasonably well as a way of aggregating the actions by chapter. But it's not a very data-driven approach. And in the kind of setup we have here, where we're trying to surface information from the data and the computation into the user interface to make it something more self-explanatory, that obviously doesn't help us because we can't surface information that isn't there. So in this case, we just don't have information about the chapter names. But I can tell you that chapter 7 is international dimensions, I think it's called. So if I put my mouse over that purple segment that was highlighted, I can see that there were 6 actions on the left that count as recognized but not addressed, associated with 4 risks from chapter 7. And I can see the reason that these things were highlighted is that 3 of those 6 risks were assigned to DEFRA, and DEFRA was the government department that I selected on the right. So I'm able to see these overlapping data dependencies, and that explains why we get this kind of shared highlighting between outputs and inputs. So I can do that the other way around. I might pick, for example, chapter 5, which I think is health, environment, and communities, or something like that. And then I can look at how that intersects with various government departments on the right. Okay, so as you can see, there's quite a lot of complexity in the user interface already in this simple example. So the claim here isn't that if you're a policymaker, your life is going to be radically easier on the basis of this. What I hope it does convey is the kinds of queries that we can support if we have this kind of infrastructure. Okay, so this is the code that we use to produce those visualizations. I don't have time to go into the syntax, but it's basically a Python-like pure functional language with first-class functions, lambdas, records, and data types. list comprehensions and other kind of familiar features. But the key takeaway is that the programmer doesn't have to think about any of those interactions I just showed you. They just describe how to map data to visual elements. The runtime analyzes dependencies and adds the interactions we just saw, and then the user can interact with the output to pose queries. So the second thing I want to show you now is something we call transparent text. So as I mentioned at the beginning, policy reports, scientific papers, and so on make a lot of the claims they make using text. But this text is very hard to interpret as well, in the same kind of way the charts are. There are things like graded adjectives, there's iteration, there are whole part relations, there's implicit reference, there are quantitative expressions all over the place. So the research question we're asking here is, can we enable this supporting text to be transparent in the same kind of way that I showed you a minute ago with visualizations, so that it can be data-driven, self-explanatory, and verifiable? So let me show you what that looks like in that example as well. So the way I'll do this is I will go to the fluid code and I will just uncomment that block of code. And then I'm going to reload the example. Now, you'll see how long it takes to run the program and generate the dependence graph. It takes about 10 seconds. So that's one of the challenges for this research, is making it more efficient. But what we have now is some figures with some supporting text. We actually had this bit of text at the top here before, and I'll use that to show you what I mean by transparent text. So if I put my mouse over the number 61, we can see that's not just a literal in the text, it's actually being computed by a query over the data. And if we look at the code for this document, we can see that it was computed by calculating the length of the nub, meaning the kind of equivalence class of the risks, or rather the risks up to their name according to risk, or this risk or opportunity descriptor. And the reason for doing that comparison on risk or opportunity descriptor is so that when I put my mouse here, we actually see that data. Otherwise, if, for example, we just considered the length, then the actual name of the risk wouldn't be relevant. So this is a way of surfacing that information into the user interface. Now, you may have noticed there's a little underscore highlighting on the committee's priority risks down at the bottom. So if I click on this number 61 and then put my mouse here, we'll see that I can now see the priority risks as a subset of the overall set of risks. And this is something slightly different. This is what we call a link. So a link is a query that has a natural language label. So we calculate the query, but instead of presenting the result of the query, we just attach a string to that query. And then when I move my mouse over the string, then we run the query. And now I see the data that was needed in order to compute that result. So moving on, I might wonder what natural environment and infrastructure sectors means in the context of government departments. So if I interact with some of these action counts, then I can see that at a minimum, DEFRA, DESNES, and I think that's the Department of Levelling Up, are relevant because they've been highlighted on the right. And then finally, this 10% down here is a slightly more complicated calculation. It's computing a maximum, and this shows actually that the dependency information that we calculate is slightly incorrect here, because we're actually only seeing the data that was needed to compute the percentage of DEFRA's actions that were fully addressed, not the fact that DEFRA was the government department that happens to have the maximum. So that's just a shortcoming of our current dependency analysis and something that we need to address. But that gives you the idea of what we mean by transparent text. So let me just skip forward again. Okay, so the takeaway here is that, like visualizations, text can also be bidirectionally linked to related data. So there are three key ingredients to this. So first of all, transparent programming languages to make this information actually useful and provide the kind of interactions I just showed you. The second thing is what we call an interpretation assistant. So this is AI-based tooling to actually generate these programmatic interpretations. So if you wanted to write a substantial paper or a document in this sort of style, it would be quite laborious if you had to author everything by hand. And then the third component is a library of domain-specific and domain-general idioms for mapping data to textual content. And we've explored this in a recent paper that's under review at the moment, where we've looked at using LLMs to synthesize, given a document and given the data that the document purports to be about, synthesize expressions that replace certain quantitative or semi-quantitative expressions in natural language with code that computes them from the data. So we can think of this as happening at dissemination time. I might be a publisher or an author, and I want to produce a document that embeds the evidence base into the document. But interestingly, I think we can also think of it as something that happens at what you could call assimilation time. So I may just be a reader or a reviewer, and I'm trying to interpret a document in terms of the data, and I might want to retrofit that document with the computational interpretation as I go along. So I mentioned some of the challenges that come up in this approach. So there are some problems in the dependence graph as currently designed. We implemented something a few years ago that gives us a kind of more fine-grained dependency analysis and allows us to reach into kind of parts of larger structures. That turns out to be problematic. So I think we have some idea of how to fix it, but fixing it is going to introduce problems of its own. It's going to sort of broaden out the dependencies quite a lot. So I think we've got some techniques for how to deal with that. So that's what I'm referring to here with this idea of scoped queries and relative queries. And then to speed things up, we've got some ideas on how to use techniques, perhaps inspired by automatic differentiation for building the graph using compilation-based techniques. Okay, and then the other kind of aspect of improving the kind of correctness and performance of the system is, I think, moving the language closer to the problem domain. So, for example, having proper native dictionary comprehensions, kind of native multidimensional arrays and columnar operations. So you can, if you're a functional programmer, you'll be used to writing these sorts of things, perhaps using lists or something like that. When you're using a dependency tracking language, you want to have the kind of domain that you're using to express a solution to a problem to be as close as possible to the actual appropriate solution for the problem. Otherwise, you end up with a lot of noise and inefficiency. So I think the way we're thinking of this is as converging on a functional dialect of Python, which has a native query language. So the last challenge I want to mention are challenges around usability and interpretability. So one of the things I haven't had a chance to show is the ability to look at intermediate stages in the pipeline. So we saw that kind of input-output relationship before, but a lot of the interesting work that goes on in computational analysis is kind of in these intermediate steps that we often see in notebooks. So this is some work that we presented at the live workshop a couple of weeks ago, and we're now writing up in a paper which allows you to look at intermediate steps in a computation and also interact with those and look at the upstream and downstream provenance relationships. And then this second thing is something we call intentional provenance. So this will probably build on the improvements to the graph, dependency graph that I mentioned a minute ago. So this is the idea of enriching the provenance information with information about the actual operations that took place. So this, on the left, this image is a screenshot. This is a mock-up on the right, inspired by spreadsheets. And again, this is a reason to produce this kind of interface. We would probably need the solution to be expressed in a language quite close to the problem domain. So you would need things like columnar operations, pivoting, rolling up along a dimension, and so on. So if the program were expressed in this very kind of data transformational sense, then I think it's plausible that we could generate some kind of user interface like this. So that's where I'm going to stop. Thank you for your time.
Questions? Please, can you come out? It's for the recording later. So the mic is over here in the front.
Okay, this is really neat. Thank you. I'm curious. Can people hear me? Is this? Or it's only for the recording? It's not. Testing, 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 testing.
Yeah.
Okay. Okay. So I'm curious what the scientists or the users have to say, right? So, are did you start the project when they said to you, "Hey, we got to have more transparency. How can you help us?" What was the motivation, and how are they responding to these kinds of tools?
Yeah, that's a good question. It's very much the other way around. So it's more like this would be a cool thing to do. Oh, why don't we also use it for transparency in data science? But more recently, we've started to speak to actual people interested in this kind of space. So that collaboration I mentioned where we're looking at this policy document, that's a researcher who works in the climate space in policy and risk adaptation in particular. So what we wanted to do there was pick an example that's actually quite hard for us in various ways, but potentially has an actual stakeholder or a user who cares about it. But that's a direction we've only really started pushing on recently.
Thank you.
Thanks.
Thanks, Rory. That was a really cool talk. Simon Payne-Jones is really proud of the fact that he put lambdas into Excel, and Excel is a really widely used tool. Have you considered kind of transpiling this into just a spreadsheet so that you can take advantage of all the data dependency stuff there?
Yeah, that's an interesting idea. So there's a project at Cambridge, actually, that Alan Blackwell, I can't remember the name of it. Do you know what I'm talking about?
I know Alan Blackwell, but not the name of it.
Yeah, so there's something, it's actually very cool, and I don't know whether they've implemented, it's a spreadsheet system, essentially, for visualization, where the visualizations themselves are kind of little spreadsheet type things. I've forgotten the name of the project, but and I don't know whether they've actually implemented that by taking some kind of open source spreadsheet and sort of hacking it, or whether they've just come up with some proof of concept of their own. But yeah, I think that's a really interesting idea, and I think where I was going towards the end with that mock-up, the more I kind of think about that mock-up, the more I'm kind of less interested in traditional programming languages, and the more appealing it seems to just think about sort of a data transformation language more natively, what that would look like, and a visual language, a language that already has a visual presentation kind of built into it.
Let's thank the speaker again. Excellent. So Patrick is going to tell us about what we talk about when we talk about scientific programming.
Thank you very much, Casey. So this talk is a little bit more higher level, a bit more abstract than the talks we've seen, but I don't think I could have asked for two better talks to follow in terms of what I'm about to talk about. So a lot of the work that I've been doing at Cambridge has been related to tools for scientific programming, but I didn't stop for a long time and ask myself, well, what even is scientific programming? And I think trying to come up with a succinct definition is quite hard. And particularly, I think, we might run into difficulties here with the scaling, but we'll see. We can run into difficulties whenever we try and come up with some kind of exhaustive list of what scientific programming is, where we might try and enumerate all the different things that might constitute scientific programming, whether it's climate modeling, data science, geospatial analysis, all these things. They seem to fit the bill, but they're all quite different. And I originally started from a place of wanting to say, what do they have in common, and maybe how do they differ from what we might consider conventional programming, something like building a high-performance web server or something like that. And I think there's definitely merit to doing that sometimes, but I think you'd be able to find some version of scientific programming that actually is very close to doing high-performance web server work. So instead, I think an interesting way to look at this is to focus in on what makes it scientific to begin with, instead of the programming aspect. And so thinking about that, I think leads to trying to think about the scientific method itself. And there's been some work by a few different people on trying to link the scientific method into scientific programming and come up with actually these properties that are inherent to the scientific method, and then ask ourselves, does our scientific programming adhere to these properties? And that's both in terms of the data and the code. And so often things that come up are things like falsifiable hypotheses, repeatable experimentation, and also reproducible methodologies. And so the distinction between those last two things, which I find hard to understand, I think, is that the repeatability is kind of, given the exact same experimental setup, can we get the same results? And the reproducibility is more, given just the information on how someone did something, can we go away, build our own version, and get the same results? And those two things are kind of equally important and obviously quite interlinked, and can be interchanged in some scenarios. So I think a useful set of axes to think about, these different ways that we might adhere to these properties, is in the data, the code, and in the programmers. And I wanted to talk about the data first. And so this has gone slightly off screen, but hopefully there's enough on there to be able to see what's happening here. I realized that I gave a talk last time at PROPL in 2024 where I showed the same slide. And late last night, I realized I had not adhered to my own kind of wants to keep things updated as new data comes out. And I had the 2022 data set. And so late last night, I wanted to update this to 2024. And to give more details on how I actually went about that, it wasn't easy because I didn't have the code lying around. And I realized I didn't have my SSH keys on this laptop. And so there was, for me, a late night phone call to my partner asking them to send over an encrypted message channel, my SSH keys from my MacBook that's back in Belfast. So I could log into a server that's in Cambridge, so I could find the script that I could put into Google Earth Engine and rerun the results for 2024. So I think there's a lot of work to be done. I think even someone who's been in computer science for 8 years is still making these kinds of mistakes. Is probably, hopefully not just my fault, and hopefully more symptomatic of the tools that we have. Unfortunately, the actual results from this are not good at all. The previous slide is exactly the same year, so it's 2008, it's Indonesia, and we're looking at the different land classifications for forests. And so the main thing to see is that orange is deforestation. So for exactly the same year, but just an updated version of the data set, there's been a lot more deforestation classified. And that's due to lots of reasons, like algorithms changing, more data becoming available, more sophisticated analysis, higher resolutions, these sorts of things. But when I updated it from 2021 to 2022, all the way to 2024, instead of this initial 3% increase from 2021 to 2022 data set, it's actually now 8.5% increase in the amount of deforestation in Indonesia. So if there's any analysis out there in the world that made an assumption that they were going to use the 2021 data set, and now they update to 2022, it's probably going to have really significant changes if they're interested in deforestation. So if the data set changes, what about the published conclusions? And I had a published conclusion last year in PROPL, and I've updated it, but it wasn't necessarily very straightforward. On this page as well, I think is perhaps a useful conceptual model for how we might think about just 3 possible ways that our data is changing or is different. And I think that's size, privacy, and dynamism. And so here, I think is a good example with this data set in that it's very large. It's, I think, 10 meter or 30 meter resolution, but it's for most of the tropics. It's not being updated that often, internally maybe monthly, but kind of to the public every year. And it's very publicly available. But how do we then work in those different axes into like how we publish something? For example, how do we make a slide deck for PROPL? And I think the work that Rolly's doing is kind of related to that, but is not quite there yet in terms of authoring. Yeah. So moving on, the code is also another place where we should be thinking about, is the code repeatable, reproducible, and adhering to the idea that we can falsify hypotheses. I really like this quote from Baxter et al. On what is a research software engineer and what is kind of their job and what do they do. And kind of expanding the quote from what I've used previously, I was happy to see that they were also talking about the same principles within that work, like things being repeatable and meticulous. But the best part is probably that no one with the same casual attitude to experimental instrumentation as many researchers have the code would be allowed anywhere near a lab. And my own mistakes from last night kind of are perhaps relate to that. But I think it's a good thing to have in the back of our minds whenever we're thinking about how code can be used in the scientific method. It is not just, it's not something standalone, it should fit into that, and there's different ways that people build hardware or pieces of equipment like telescopes that have very accurate kind of data describing how they can be used and the precision they have, and yet we seem to just throw code about willy-nilly over the internet. And so I thought some questions might be useful. In what ways does writing code for scientific programming differ from conventional methods? And I think one of the main ones is that eventually there is usually some form of communication at the end. And we see that in things like literate programming. And that really does change the control flow of how we might execute a program. No longer are we writing a program and eventually we're going to run it as a standalone application. We're now discretely executing chunks of our program in an exploratory manner. And maybe we should be thinking about programming languages and tools that actually have that baked into them, unlike things like Python, anything inside a Jupyter notebook, where quite commonly people make mistakes where they change something later on that's actually doing some kind of mutation of data, and they run something from before, and suddenly they get different results. And then another question is, are the ways in which we publish and distribute software amenable to the kinds of things that we want for the scientific method? And I think the short answer here is that that's not true. I think we don't have the reproducibility that would be required for something to be considered a scientific method, and we can do a lot better. And I think we have tools that can get us a long way, like Docker, like Nix, and these things that offer some way of locking down all of our dependencies. But these are not necessarily extremely accessible to the programmer. And that is the last thing that I want to talk about, which is that the domain in which we're working in is not necessarily full of computer scientists. It's full of what Mary Shaw calls vernacular programmers. These are people that program by necessity, not kind of through choice, or they may choose to, but they're not necessarily coming with the same backgrounds as we might all think that our users will have. And so I think it's important to remember this whenever we are designing the tools that we're hopefully going to put into the scientific programming world. And in particular, I think we should be looking to have a tremendous amount of empathy for vernacular programmers, or people that don't know what necessarily a hash is, or don't know a Merkle tree, or these sorts of things. And so I think, as I said at the start of my talk, I'm really pleased to be following 2 other talks that I think actually do adhere to all these things. So I think it's great to be seeing that. I'd like to just round off with some of our own work that hopefully is looking at doing all of these things in some way, which is building a kind of shell session manager that builds in reproducibility and the ability to undo your mistakes, which is at the moment called Shelter. The idea behind this tool is that it has tremendous empathy for the users in that many scientific programmers are already having to use shell scripts and use a shell to do their work, but it is quite a unforgiving kind of environment to be doing your work, where there's lots of ways to do very destructive things without any way to recover from that. And the idea with this tool is that actually we can use all the things that we've been talking about already and provide a similar kind of environment where we're not asking people to learn too much more, but provide a lot more kind of low-level systems that are helping them. So for example, here, we're able to create 2 different distinct sessions, and later on, we're able to bring them all into the same place. Other things that are going on under the hood here is that all of the dependencies are being tracked for how files come into existence and the things that might be used in order to do that, and we're able to do that on kind of modern systems using things like eBPF. There's also the ability to merge different sessions, and so this can do the same analysis based on reading and writing to know that is it safe to do a merge, or actually should we replay what we've done because there's been changes in the dependencies. This is still very much work in progress, and I hope to keep the principles that I've been discussing kind of as part of the design of this going forward. That's the end of my talk, and thank you very much for listening.
Thanks, Patrick. That was super interesting. I really love Shelter, by the way. I want to hear more about that. But my question was actually about the kind of framing you had for the exploratory kind of programming, which I really liked as well. So you were talking there about kind of, you're often in this exploratory mode where you're not running the whole program to produce a kind of output. You're running a little fragment and seeing what happens. Have you also thought about that as a kind of end user affordance as well, like as a kind of comprehension tool? The world we live in now, it's very much, you have a static image or some kind of static output, and comprehension is, something that has to happen inside your head. It's not some kind of interactive relationship you have with the artifact. And I'm wondering if that same intuition you gave for programming could extend to kind of how I actually understand what I'm looking at. I might sort of tweak an input, see how the visualization changes, for example, and that's part of how I'm making sense of the actual.
Yeah, thanks, Rolly. Yeah, I definitely agree with that. I think that it all becomes, publishing things is stuck in the past a little bit. I think being able to provide end consumers of the information or the scientific things that we do with kind of the full artifact would be super useful. So one thing with Shelter in this particular example would be the ability to basically give them the entire or some portion of the entire execution environment for you to play around in. Likewise, if you can do that all the way through to the actual authoring tools that you're making, it would be great to be able to just do that in a web browser, for example, and not have to leave the comfort of the place where you're actually consuming the information. It gets really tricky depending on how big your data is, and as I was talking about before, those axes of what the data are, so the size, the privacy, and the other one that I've forgotten. Dynamism, right, which is maybe not as related in this instance, but if it does update, you would want to know that as well, so you can go back and check whatever you might add.
Thanks for the talk. I'm wondering what your thoughts are about what the goals should be or what the end game should be. So we sometimes try to compare scientific programming to lab science. So you had that quote by Baxter, right? On the other hand, lab science is problematic in various ways and is constrained in various ways that software is not, right? Like you combine 2 chemicals and that can result in an explosion. You can do all kinds of things in software without that kind of risk. So there's an opportunity for a lot more exploration. And we still have problems in the lab where you can't actually reproduce the experiment, right? Works in my lab, doesn't work in your lab. Why is that?
Yeah, that's a great question. Thank you. I think one of the things that I find probably the most frustrating is that I don't think we need necessarily a lot more tooling. I think there is like a social aspect to this. That is that some of the things that make it hard to reproduce someone's results is just like, it's quite opaque. It's not, the code is just not available, or the methodologies that we write are so far removed from the code that we don't actually know, we can't reproduce it because it's not kind of precise enough. So I think trying to get more things like artifact evaluations into publishing conferences, both like ICFP does, but also in kind of more sciences that are using a lot of computation would be great. As for kind of more future plans, I think is similar to what I was saying to Ruli, which I think is kind of the ability for the actual ways that we publish kind of these results to be more kind of cognizant that it was made in a computational way, and having that actually part of the way that we author the end goal. So for example, here, presenting these slides, all of this is incredibly static, and I'm having to put in all the links to say, go and look at this source code, this thing was run on GE, and like you can come to me and I can give you that script, but there's no way for me to take the typesetting kind of languages that we have, whether it be LaTeX or types or something like that, and kind of have a really deep integration with also the data and all of the computation that went into it. So I think some kind of more unified framework for that would go a long way to helping this as well. Yeah, thank you.
All right, let's thank our speaker again. Yeah, you can. It's on now. We can't see it. Yep. Should go to. Yeah. Display. Yep. You're done. All right. So we have Cyrus telling us a fair case for a computational live computational problem. Off you go.
Hi, everybody. So this is joint work with Michael and Anil, and this is also a talk that I think is situated very well within the program, follows very well with the talks that we just saw. So the motivation for this work is that scientific workflows are increasingly collaborative. Okay, so they're increasingly large-scale collaborations, and they're increasingly loosely coordinated large-scale collaboration. So you might have various field and experimental scientists collecting data, and this is a continuous process. Maybe it's actually coming from things like satellites in climate science. And then you have data scientists cleaning and analyzing this data and publishing these analyses. You have model builders, computational scientists, parameterizing system models using this data, and then other model builders integrating these systems models into integrative systems models, kind of bigger models of bigger systems. And these might go on to inform various parts of society. So environmental interventions, both public and private, public policy, public engagement. And so collectively, this whole thing can be understood as a sort of collaboration that's ongoing. And These workflows need to be supported by tools. And to support these kind of workflows, the community, maybe used to be called the open science community or the scientific community, has identified a lot of best practices around scientific data and scientific code. So the ones I want to highlight here fall under the rubric of the FAIR criteria. So this is a set of criteria that's pretty well established at this point. And so let me just tell you about these criteria. So the FAIR stands for, one, findability. So this is just stating that we want data and code to be discoverable by the people and the machines that can make use of this data. Closely related one, I think they're really only different to make the acronym work, is accessibility. So in addition to being discoverable, you have to actually be able to retrieve it. Okay, you have to access that data that you found. Now there's a little bit of subtlety there because sometimes access is controlled in some way, right? So maybe they are truly different criteria. A big one is interoperability, right? If you want to have collaborative workflows, you have to be able to actually interop with the data sources, the tools, the code that other people are using, and there's a lot of diversity in the tools that we use, and so this is a major challenge. And then under R, R stands for reusability, but I'm also going to throw in reproducibility under this rubric as well, although it's often discussed separately from the FAIR criteria. So it should be possible to run, or in the reproducible sense, rerun, and modify and build upon these artifacts. It's not about just using them as is, but about making modifications to them and adapting them to other purposes. Okay, so those are the criteria that are kind of central to this talk, and then I'm going to throw in one more that Patrick actually just highlighted in his talk, which is that you have new data and new models arising constantly, especially in climate science, right? And so we want to be able to not just get snapshots of an analysis at a particular point in time when a publication was put online, but rather to be able to easily and quickly and kind of automatically, ideally, update these when the data or the models change in some manageable way. Okay, so fairness and liveness is what I'm going to be talking about here. There are other things we care about as well, but those are the focus areas for today. The core problem, the central problem kind of animating the work that this talk is about, is that scientific software tools sort of have bad defaults. So this usual patchwork of software tools that we use to do scientific work, these are often just kind of adapted from other kinds of professional tools that have been developed. They require actually putting in extra work to follow these best practices. So if you just use them in the sort of the normal way, if you're just a graduate student and you're not thinking about the FAIR criteria and liveness and stuff, you're just thinking about your next publication, you're doing some modeling of fish patterns in the ocean, right? You're not thinking about these things. You're not going to put in that extra work. And so the defaults really matter. And we know that the defaults really matter in general in design, right? This is something that is well understood. And we have bad defaults. The tools that we use today are not designed to support these kind of collaborative scientific best practices by default, and so often we don't achieve these criteria. And so let me consider a particular tool as a central example here. So the tool that many scientists use is very central to their work is a computational notebook system, something like Jupyter or its various cousins. Okay, so I assume most of you have seen Jupyter before, but if you haven't, it kind of looks like this, right? You have code, and you have figures, and you have various authoring things going on here. And what you do as a scientist is you kind of do your day-to-day work in Jupyter. And let's analyze this from using these criteria. And so I'll argue that in some sense, Jupyter fails in all of these ways in terms of its default usage. So findability and accessibility, by default, when you create a Jupyter notebook, it's just sitting locally on whatever machine the Jupyter server is running on. And you have to put in a lot of extra work in order to make it public and accessible in some way, and it's actually quite tricky to do that. Interoperability, so one Jupyter notebook, even on your own machine, can't really access another Jupyter notebook. The code, the data on another notebook is not easy to access. There are kind of hacky mechanisms to do this, but it requires just re-executing that one notebook in another. Even if all you want is some helper function that was defined in the other notebook, you have to rerun the entire analysis, and then you end up in an environment where you've rerun it. So interoperability in that sense doesn't really work, and so often, you don't interoperate, and you end up copying and pasting a lot of things, and it takes a lot of extra work to turn some a bit of an analysis into a generalizable library. And often these are skills that many scientists don't have, or they don't have the time to bother to like turn it into a Python library and put it up on the package manager and so on. Reproducibility and reusability. Notoriously, computational notebooks are not reproducible because of the imperative programming model there, and you can execute cells out of order, all those kinds of things. And then I just talked about some of the reusability issues there as well. And then liveness, right? So you actually kind of just get a snapshot of the notebook as it ran the last time it was run, and when new data or models arise, these things aren't linked in any really direct way, and so you have to rerun everything yourself, and if they're linked using copy and paste, for example, then updates in one place aren't going to propagate to the other place where that same logic might exist. So these criteria by default are not satisfied by notebooks, and I think that causes a lot of problems. So we've been doing a lot of thinking about kind of the future of scientific workflows. And we have a proposal, and this paper is really more of a proposal and kind of a description of ongoing work and ongoing thinking that we're doing. And so in this paper, we propose this system called Fairground. And what Fairground is it's a computational commons where we imagine thousands of scientific artifacts, to include notebooks and papers and data sets and things like that, are authored, collected, and maintained collaboratively in a form that is executable, interoperable, and that maintains these FAIR criteria and liveness through default usage, through the normal usage of the tool, without having to put in a bunch of extra work. And I think that's really the critical thing that I want to communicate here, is the defaults really matter here. And so let me talk to you a little bit about this idea. And this is really just a start of a conversation. So I'd love to talk to you all about how you would like such a system to work, and what some of the criteria that you would have in the domains that you all work in. So what do I mean by a computational commons? Okay, so I like using this phrase. What do I mean by that? So it comes from the phrase kind of a commons, or in particular, we're inspired by other digital commons. So of course, you're familiar with digital commons like Wikipedia and GitHub. Scientists often develop digital commons to collect scientific data sets and code repositories that are contributed to these commons. And the idea is, you want people to work together to develop these shared digital resources. But what's missing, I think, in a lot of the digital commons that we have today is computation. So even GitHub, and certainly something like Wikipedia, it's really just a place where you put kind of the results of a computation, right? You put in, you paste in a table or a figure. Or with GitHub, you might put in results, or you might put in the source code, but the computation and the configuration of that computation and all of that stuff is somewhere else, right? And I think that's really not the right way to proceed in the future. I think the future digital commons must be a computational engine in some way. It must compute kind of natively, and the computation has to live together with the data and the code. And so here's kind of the provocative thing that we want to think of Fairground as, is we want to formally think of it as a single massive program, a single massive live program. So a program that's being edited and executed continuously. And this editing is happening collaboratively by thousands of contributors. So we imagine thousands of humans of various persuasions, right? Scientists, journalists, scientists with various expertise, not just computer science experts. And then increasingly, I'll just mention, of course, that safely sandboxed AIs are kind of an important part of the vision for the future of computing, and we want them to be participants in this collaboration as well, with, like I said, safe sandboxes to operate within. So how do we build this single massive live program, and what are the research questions there is kind of what we've been thinking about. So last year at PROPL, we introduced some of these ideas, and we discussed the user experience, like what would it feel like as a user to work within such a commons. And we really don't want the user experience of this to feel kind of foreign to scientists. We want it to feel like working in a notebook or working in an authoring environment, editing a wiki, a Wikipedia page, something like that. And I think there's been a lot of interesting ideas. I won't go through all of the ideas that we discussed in the paper last year, but take a look at the PROPL talk that Alexander gave last year for some great demos. But you can see here that there's different users, maybe journalists and scientists. This kind of looks like a paper, except in the sense that kind of Rolly was getting at. We incorporate computation into this directly. So if you click on a histogram here, you can actually see the code that generated it. Maybe you can actually manipulate it in some way. We imagine a system where you integrate both graphical editing and symbolic editing together, and we've done various work in that space. So things like these sliders and bar charts are all part of the code. They're not sitting separately from the code. Okay, so the user experience, I think, is a really important aspect of this. You can't really introduce a new system like this if the user experience is bad, and I think so. UX has to be part of the design from the start. But this PROPL, what I want to discuss are some aspects related to languages and systems, that the underlying systems that would go into building something like Fairground. So the most obvious question, especially in a community like this, is if we want to write a single massive live program that's being collaboratively edited, well, what language is that single massive live program being written in? Ah, great. So, I mean, I think the answer is obvious. Like all great scientific software, it should be written in Fortran. Okay, see you later. Well, I also heard OCaml, and I didn't hear Python, but probably many scientists would say Python, and other scientists would say R, and others would say Julia, and others would say MATLAB. And then there'd be the grumpy one that would say, I write all my code in C, right? So, and then of course we would all say OCaml, right? So, I think this is a really important question, and it's one that we have to confront as a community, right? That these languages all exist. They all have large communities with, large fan bases in the scientific community, and people aren't really ready to give up on the languages that they work in. And I say this as someone that, I design new programming languages. I'm really kind of not excited about existing languages. We really have to confront that problem. And so I think the real answer to this question is yes. Okay, so in other words, I think what we need is an orchestration language that supports this mission of a single massive live program. And one of the central kind of aspects of an orchestration language is that it has foreign function interfaces to various existing languages that people use in the community. And maybe this orchestration language is one in which you can kind of hope people transition to, it's maybe more native features in the future, but this FFI problem is one that I want to discuss quite a bit. Okay, so if we're going to design an orchestration language for Fairground, let's talk about its design and its implementation. So what are the design and implementation criteria for Fairground's orchestration language? And so I'm going to talk about kind of three things here. So to support interoperability, what we need is a language, like I said, with a robust and customizable foreign function interface, or FFI. And I also think we need to think very seriously, not just about foreign functions, but about foreign data interfaces as well. So I'll talk a little bit about that. And then interoperability, I think it requires some sort of data format for, what is the common data format across the system. And I think there's been a lot of work across computer science on data formats. I think as a programming languages community, we should really kind of embrace the essentials of type systems here and use type systems as the core of interoperability. And so I'm going to talk about those things. To support these criteria of reproducibility and liveness, we need to not allow computations to kind of go willy-nilly on the entire world, but we need to instead control dependencies that these computations have, because we're going to be working with code that has maybe even conflicting dependencies, and we need to control side effects. It's really important for reproducibility and for liveness to not just kind of allow the code to have irreversible side effects, on the world. Also, to support liveness, in particular liveness at scale, we need the implementation of this language to scale in various ways. And so if we have a program that's being edited constantly by thousands of people, we can't have any kind of operation that happens in a batch way across the entire program. Think of a program the size of Wikipedia. We can't have every edit to it cause a retype check of the whole thing. And so we need incremental, parallel, distributed, and what I call gap-free, meaning like if there's a bug or there's a missing piece in the program, it can't all shut down. So gap-free, type checking, and program execution, and anything else, program analysis, etc. So I'm going to talk a little bit about all of these things, and I'd love to talk more about all of these things throughout the week. So let me start with the foreign function interface, and in particular, there's kind of an interaction between the FFI and this kind of need to control dependencies and side effects. So the problem is FFI systems, like even for pure languages like Haskell, often just kind of let you do whatever you want in that foreign code. So they permit kind of uncontrolled code execution, and the stuff that happens in that foreign code can inhibit these criteria that we care about: reproducibility, incrementality, parallelizability, etc. And so what we need to solve as a community, and I don't have a solution to this, but I have maybe kind of the direction we need to go in, is we need a language with an FFI where foreign code must, and truly must, one, execute in some sort of isolated execution environment where the dependencies are managed in some way. And so I think it would be a good thing to explore using a build system designed for reproducible builds, for example, Nix. And I think there's other candidates here as well to consider. And then two, the side effects of this external code need to be controlled in some way. So obviously when you run a simulation, it needs to access hardware, it needs to access file systems sometimes, things like that. But if we can kind of encapsulate that and treat those as kind of internal effects, then what we need to do is ensure that the interoperability with the rest of the commons, all the other codes, or the stuff coming into the simulation and the stuff coming out of the simulation, it's mediated by this pure typed functional interface, and the side effects are kind of managed in some way, so that ideally you have reproducibility. When you run it with the same inputs flowing in from the rest of the commons, it gives you the same output, and so you can manage it as kind of a foreign node in your data flow graph, something like that. And so I'm not really aware of a lot of work on really kind of pure FFI systems, like systems that really try to manage the foreign code in this way. So I think that's something that would be really interesting for us to work on. And if you're aware of something I'm not aware of, please let me know. Okay, so that's the foreign function interface. I also want to talk about this foreign data interface idea. So the problem is, data in scientific work is often very large, right? It could be petabytes of data out there. It's often stored externally in some way that is very expensive. So it's not realistic to just kind of pull the entire data set into the commons, but rather we need the runtime system of the commons to pull kind of as needed the bits that are needed for the computation that's currently being expressed, or even to push computations to the data sources. So often you have data sources that support queries in some way, or that can run certain computations locally. And so we want to take advantage of that and not have this sort of like world where everything has to be pulled in. And so I think this actually needs to be built in at a pretty deep level in the system, where you have a foreign data interface, kind of like a foreign function interface, where the foreign data is described using the type system, but it's not actually, the values don't exist in the code, but rather are accessed via some sort of customizable access protocol. So how do you access that data? Is it some sort of web query? Is it something else? And then how should the live runtime in particular, if we want this thing to be running and updating live, how should it determine when the data that you're depending on in this foreign source has changed in some way? Can we trust that it's immutable and so we never need to worry about it changing? Or does it update every day from a satellite? Or does it need to be polled every 12 hours or something like that? So I think all of those kinds of configurations should be part of the commons and kind of used by the foreign data interface system. And then, I think there's opportunities to integrate with systems like Spark or other functional data flow engines that have been designed to intelligently query large data sets and even to push computations out to these data sets when appropriate. So Spark has this push down API that's, I think, really interesting to think about here. Okay, so I think there's lots of interesting questions in how do we work with foreign data in a programming language. And then finally, I want to talk a little bit about liveness at scale. And so this problem of having all your tooling really work on arbitrarily large programs, and in particular your type checker and execution engine needs to be not just incremental to small changes, but constantly updating in response to small changes. Like imagine if Wikipedia were a program, there's little edits to Wikipedia every millisecond essentially, right? So we need an engine that supports that, and I don't think we have such a thing in computer science today. We also want kind of auto-parallelization. There shouldn't be an inherent order to all the scientific code in the world. That makes no sense, right? We want it to be distributed across all the hardware that we have access to at our institutions and so on. And we want this kind of gap freedom as well. And so there are a number of open problems here. One thing I'll point out is the type checking problem is something that we've, I think, addressed in theory. So if you're interested in how we do incremental and parallel type checking, we have a talk this Thursday at 2:15. So Thomas is going to give this talk on incremental type checking. I think it's really cool work. It won distinguished paper. Hooray. So we're working on scaling this up to full-scale languages, so it's solved in theory at least. But we think the type checking problem is something we have a handle on, although there's probably more open problems here. An open-ish problem, I think, is the execution side of this. So if we're modifying this program constantly, we need to be only re-executing exactly what needs recomputation. So I say it's an open-ish problem because there's relevant prior work. We have some prior work on live programming with holes where we can execute programs as they're being edited and are partially complete. There's been work on incremental and parallel build systems that's relevant here, incremental and parallel spreadsheet execution. There was a number of papers on that problem in the past several decades that I think are relevant here. Auto incrementalization and parallelization for functional data flow has had a lot of work put into it, but things like Spark. So I think integrating all those ideas and expanding these ideas into just really a general incremental and parallel live execution engine for a general purpose language where we do make the assumption that the program itself, not just the inputs to a fixed function, but the programs itself are changing every few milliseconds, I think, is important. And because some of these recomputations are going to take time, we want to intelligently handle stale prior results. So awaiting upstream recomputations, can we indicate that in some way and still give access to prior versions of the results with some kind of flag on it? So that's all I wanted to talk about there. So those are some of the things that we are thinking about. We're working on some aspect of all these problems in the Hazel project, so we're open to collaboration there, but we think these are also just general problems CS folks should be thinking about in whatever setting they work in. And then I'll close with kind of just a note on AI and how that integrates with these ideas. So I think AI actually creates an opportunity, a unique opportunity for a new computational commons. So if we have such a system, right, if we've solved the PL and systems and HCI problems, I think AI will allow us to rapidly ingest a large amount of existing code and data into this commons kind of semi-automatically, which, the network effects will be maybe lessened in that. And then I also think AI will work better within such a commons. So we had a paper at UPSL last year where we showed that kind of using a semantic context is really helpful. So I'll kind of stop there, or let me just kind of mention. So I think all of these criteria can be addressed in such a system. Findability and accessibility is kind of inherent to putting everything in a commons. You have to think about access control. We talked a lot today about interoperability and reproducibility and liveness. So I think there's really the ingredients for all of these things to be kind of addressed by default in such a system. And so I will stop there.
How are you imagining the kind of what you call the foreign data interface would need to be like in order to support liveness at scale? Do you need to kind of potentially maintain in data information about what's changed? So for example, if I've got a large data structure that's changing, I don't want to recompute, because there's a whole bunch of downstream computation that depends on the whole matrix or whatever it may be.
Mm-hmm.
I may know that just one cell has changed.
Yeah.
And I might just want to sort of publish that information as part of the revision to the data. So do you think the foreign data interface would need to support that notion?
Yeah, I think the foreign data interface should have some pretty kind of fine-grained way to express change. If you don't have some, the right information to express the fine-grained change, then you can do some coarse-grained kind of analysis. But ideally, maybe some of your work on kind of provenance is relevant here. If we can really kind of capture what exactly changed, we can, and then, forward that through all the dependency analyses, I think that would be really ideal. Yeah.
In the interest of time, may I ask other questions to be discussed over? Let's thank the speakers.
thanks. So today I'm going to present early work on an attempt of verification in climate models, especially for an orchestrated software piece, which is a couplers in climate models. So to start with, what is a climate model? A global circulation model, which is a type of climate model, are these large-scale models that simulate Earth's climate over a period of time. And these models usually tend to use a lot of physical laws, be it your fluid dynamics or thermodynamics, and they use several numerical methods, and they operate on a large scale of observational data. And most of these climate models are implemented in large Fortran, and due to like huge computational demand that they have, and the codes run on supercomputers. And climate models are usually composed of many interacting submodels, be it your atmosphere, land, sea ice, or ocean models, which are sort of interacting with each other, exchanging data with each other. And each of these submodels run on a different grid, different time step, different spatial resolutions. Now, in this figure, we can see that there are 4 distinct climate models, and all of them, we can see that they are different subsystems operating with each other. And although the scientific goal of all of these climate models are sort of similar, but the architecture differ in how the model is orchestrated. For instance, in the first 3, we can see that the chemistry model is subsumed in atmosphere model, whereas in the last one we have a sea ice, which is subsumed in atmosphere. So there are like a difference in how the models are orchestrated together, but there is also sort of a similarities that is in the center of all of these climate models. You can see a coupler which is connected between the various subsystems. So what is a coupler? So it acts as a communication hub. So it helps in model interaction, where the data exchange is mediated between various submodels. And usually it performs various operations like field exchange between the models. It performs interpolation of data and conversion between one grid format to another grid format, and also the time synchronization when both of them are running in different time steps or different time intervals. How do we synchronize between 2 models? And coupler is the one which is performing a lot of these operations for different models. And so which is why it's very critical for any sort of reproducibility or scalability, and if you want to attempt for any correctness in multi-component simulations. And even some minor errors in coupler, be it your unit mismatch, that can easily propagate and distort some scientific results that we have from these climate models. So coupler correctness and verification in general. So verification of climate models is, people have very keen on this, but the only problem is they haven't get past testing or integration testing and a lot of validation. And the problem that here is verifying a full climate model is extremely complex, because it's huge, millions of lines of code, and everything is written in legacy Fortran. And coupler represents as a very tractable verification target that you can attempt to see if there can be any sort of correctness that you can offer for many models at a time. So it makes a very high impact target. And even couplers are very complex, and they are loosely specified orchestration layer, because when couplers were originally constructed, they weren't designed with a formal verification in mind. So, which makes it also hard to ensure any sort of correctness or reproducibility or even maintenance. Maintenance is like, if you have a whole climate model and if you want to replace just your atmosphere model, and how does that replacement work in the entire climate model? Does it offer any sort of correctness, or does it distort any sort of mismatches or any scientific results? Is a very interesting aspect to look into. And if with the previous picture, we saw that it's very similar to how software components work together. It's more like different modules are connected together, and it offers us to look into contracts or modular reasoning between the various models. Right now, there are these are the few major coupler frameworks that we have. One is CPL6 and CPL7 by NCAR, and we have the Earth System Modeling Framework, which also gives more like a very modularized framework for how do we communicate between the models. And in European models, widely used OASIS couplers. And MCT is more like an embedded library, which is been used in CPL6 and 7 and OASIS coupler. It basically tells how the communication pattern is done between the various models, and also like how interpolation is done, for instance, or other different other operations is done using the library. Now, the couplers, in general, they vary in design, be it a standalone coupler. For example, ECMF is a standalone coupler, whereas the MCT is an embedded library. They have different data exchange pattern, different time, how timing synchronization is done varies differently, how it is implemented is different, and how interpolation is done is also different. Probably it's an offline interpolation or an online interpolation. So each couplers offer various ways of doing this, and it has also been evolved over decades with limited specification. And we looked into a bunch of these couplers, and based on some of these couplers, we identified some recurring tasks that could guide into a general design principles and like verifiable modules for these couplers. And some of the functional modules or the verifiable functional modules are configuration and initialization module, field registration and metadata module, grid manager and interpolation module, time synchronization, and data transfer and routing module. So these form a general design principle that any coupler should do. It's more like a coupler's generic tasks to perform. So we sort of extracted a tasks or a module task for each of these coupler modules. For instance, our configuration initialization module, what it does, it parses an external configuration file where you define your source or your target or various data that is included in your for coupling. And then you have a field registration and metadata module, which manages each coupling field and see that if it is registered and an associated metadata required for the coupling, be it your coupling frequency or timing interval, all of these data has to be registered if it is a field. And then you have a grid manager and interpolation module, so which defines various grids between the module, and you have to generate the interpolation weights for each other, and then you have to remap the grid. So for instance, if you have atmosphere data just flowing through an ocean model, so you have to remap the grid from atmosphere to ocean, right? So there has to be, the coupler is the one which is doing the interpolation and then remapping the grid. And next we have the time synchronization module, which is coordinating the coupling schedule between various modules and how the coupling intervals is coordinated between them. And the last one is the data transfer and routing module, which is the one which is actually routing your information. Either you're doing an MPI transfer or is it a shared memory transfer. How the data exchanges actually happen is based on the communication pattern is handled during this module. So I'll show like one example with one of the modules and how we extracted these tasks in a form of a behavioral contracts at the level of modules. So for time synchronization module, here the example shows with contracts in form of requires, ensures, and invariants, which takes the form of your preconditions, your postconditions, or your invariants, where your precondition here says that the components are aligned and the clocks are consistent with each other, and your postcondition says that the data exchanged are once per step and there is no duplication with the time. And also the invariant here is the time monotonicity, saying that the time is always forward moving, which is an invariant for your whole module. And this usually, it's very common. We see that a lot happening in contract expressions using JML or ANSI C specification language, which has been used with various behavior specification language, which enables these sort of contracts verification at the modular level. Now we have to address the elephant in the room, which is the Fortran dominance in climate modeling. So Los Alamos laboratory published a report saying that if you were to do some sort of migration of all the Fortran modules to Python, it would approximately take $15 million and several years of work. And still, it doesn't guarantee that it will have a bit-to-bit reproducibility, or it can't guarantee there can still be a lot of numerical mismatches. So there is no 100% guarantee that the migration will hold the validated legacy code that the Fortran has guaranteed so far for us. And there are some attempts to make some interoperability between Fortran and Python, which is available, but also comes with a lot of overhead. And they treat Fortran as a black box, and then you have an interface, and then you talk to the modern Python models. If we talk about verification, what's happening inside of verification? So Fortran lacks modern formal verification tools. So we have pharmacy for C, and we have key for language. These are the deductor verification tools, or we have Spark for Ada. But we don't have any deductive reasoning tools for Fortran, so it becomes very hard to prove any sort of automated correctness or automated reasoning for it. We have a small prototype which is done in Camfort, which goes in the similar direction of providing some sort of deductive reasoning for Fortran. And Fortran also doesn't have any mechanized semantics, so it also becomes hard to come up with the tool. So if one were to start, they should actually start from the very beginning, which is giving a mechanized semantics for Fortran. So that's where the research is at the moment. Before I proceed to what we actually do, so I'll take a simple example, and I'll show how we try to solve this problem. So this is a simple coupler interaction flow between ocean to atmosphere through the coupler. And atmosphere and ocean models, they run independently on their own grid and their own time steps, but when ocean sends the data to the coupler does the processing for you, and it sends the data to atmosphere. The processing meaning if it's interpolation or time synchronization or other generic tasks that we saw so far. Now, what we propose is a dynamic contract verification at the coupler boundary, where the interaction actually happens with the coupler. So we insert our contracts or runtime assertions that we saw so far at the coupler boundary to check for the data consistency and data flow between the models. So this is more like what are the tasks, the generic tasks that you identified at the couplers. Now they are modified into, or they are captured in the form of module contracts. And these contracts are available at the coupler boundary, where the models actually send the data. And these runtime assertions make sure that the right data or the right form of data is passed between one model to another. So it sort of guarantees correctness in how the data is processing, or how the data is exchanged based on your models of module contracts. But this also becomes difficult because of the poor integration with the legacy Fortran models. So what we do is we use the Fortran's ISOC binding for C that we have, and we wrap the Fortran with C, and we use pharmacy and its runtime verification plugin to verify these dynamic contracts, and these contracts sort of describe and validate the expected coupler interactions. So Fortran has this native support to the C, so it makes it slightly easier. But if you, for example, how we have JNI for Java, which helps for two different models to two different codes to communicate with each other, Fortran makes it easier to do it with C models. So the ISOC binding sort of, you can wrap it easily, and then you can actually get the data for the dynamic contract verification. So far, to wrap up, we see that the couplers acts sort of a coordination hub that keeps various submodels working in synchronization, and they share very common behavior despite their different design architecture, and they can be captured as verifiable modules or verifiable contracts for different operations, such as data exchange, timing, interpolation, and they form sort of a clearer design principles and for modular verification. So the idea is we can retrofit an existing couplers with these dynamic contracts, or if somebody's using a new age language such as Julia or Python to come up with a new couplers, you could use the same design principles and include the contracts in the language, and it's more like coming formal verification from the design. So it's a design by contract approach if you're thinking about a new coupler, but it could also work for retrofitting for existing Fortran models as well. So the next steps would be to actually build a minimal contract framework for existing couplers. So what I tried to did is with the Oasis coupler, which is open source, and it's available, and it's easily it has a lot of community support to be able to understand how the coupler actually works. It's not opaque at all, and what I'm trying to do is to have some sort of a contract framework for Oasis coupler and bridge some legacy Fortran system. And of course, I have to check the access, the reproducibility and performance, because it's a runtime verification technique, and how does it affect the performance is yet to be discovered. So you can find more details on our paper at PROPL workshop. So we did use a real runtime bug, which was found in one of the couple model, and we sort of assess how the error was developed, and then we see that how it could have been avoided if you had some sort of contracts placed at the coupler boundaries. And we also mentioned all the modules and how these modules could be represented as your pre-post conditions and invariants for each of these modules. So it gives more like a design principles if one were to create new couplers, or if one were to generate these contracts. So yeah, that's pretty much the talk. Thanks.
Questions? Can you come up to the mic just so that the recording catches your question?
So you said already that you don't know how it will affect performance, but do you have a guess maybe? Because I think like these models are like ultra complicated, so maybe the part in between doesn't, in comparison, wouldn't matter that much.
Yeah, I mean, I'm not targeting something at the production level of understanding this. This is more at level of when you're actually testing, and at that time, a little bit of, there is an expected overhead, of course, but I'm guessing it's a 2 to 5x of, because it's a dynamic verification plugin of pharmacy, which comes with its own overhead, but I'm guessing a 2 to 4x of overhead. Approximately.
Last question. So I have a minor kind of objection to the diagram here.
Yeah.
That kind of lends itself to a question about, like, you know, what is the right way to verify these types of scientific softwares in general? Which is that when I think of a coupler, there's a part of me that thinks that, especially within the context of these various models where they're coupling at a boundary or something, that has like a precise mathematical meaning, as say an interpolation operator or something like radial basis function interpolation. They have this whole vocabulary of these things in systems like precise. And what And so that thing would then maybe have, phrased that way, a good convergent test, or else some other property that would lend itself to testing and verification. So why not go there is kind of my question. Or is there like an example, or just a bug that you guys have found lend itself to this kind of more vision better?
So what maybe I stress more on the data exchange part here. So, but the coupler itself. Okay, let me try to rephrase what you're trying to say. So, is it more like this coupler feels, or the contract feels more orchestrated, or it doesn't really capture the real underlying conversion of how these models interact? Is that?
We'll put it another way. If I'm doing something like Radal basis function interpolation, there's a precise mathematical meaning that roughly says something like, I have this point cloud data, this is the best approximation in some sense, that's the contract that should be honored, I can test this via various pathological cases, which hit the convergence boundary.
Yeah, but also that sort of happens, but this is a bit more high level, I would say, because let's say we take the same interpolation. And this carries, you still have your interpolation or a mathematical way of doing interpolation underneath, which has been validated, but we sort of put a behavior of how this interpolation should go from one target to another. So I would say this is a bit more on a high level and doesn't really Yeah, sure.
Excellent,
Yeah.
Excellent time to stop and continue our coffee. Let's thank the speaker again.
Now, I'm going to run through very quickly some of the kind of domain knowledge that we need to actually understand what GeoTessera does and why it's useful. So, the opportunity. So we got many pressing problems. I'm sure I don't need to motivate it to this audience, but we have problems in food security, climate change, biodiversity loss, and these are all problems where having timely, accurate answers to how the surface of our planet is changing can be key to coming up with solutions to these problems. So we have these pressing problems. At the same time, we have significant amounts of remote sensing data that's freely available. Right? There's gigantic volumes of data. So we've got things like Sentinel-2 and Landsat. These are multispectral satellites, so they're a bit like you have your RGB channel in photos your camera takes. These are like that, but with some additional channels that are very useful for certain kinds of tasks you might like to do. Then we have things like MMAP. These are hyperspectral cameras. So they, instead of having 3 or 9 different spectral channels, they may have hundreds or thousands of different spectral channels. But obviously, for the spectral resolution, you trade off temporal resolution and spatial resolution for that. Then we have things like Sentinel-1, which is synthetic aperture radar. We have JEDI, ISAT-2. These are laser satellites. All this data is available. But using it is hard, right? The first thing is there's a lot of it. So a single analysis over 8 years, just using one set of multispectral, one multispectral constellation would be about 250 gigs of data for a single point on Earth. So it soon becomes prohibitive to do analyses over long periods of time at large scales. And that's if you know what data product you want. So for example, Sentinel-2, there is 2 or 3 different levels of product you could have that have various different properties, and each one has different processing baselines. So you've got to decide all that up front, and it requires significant domain knowledge to actually get started in this. But the second problem, actually, is that the optical satellites have, which is the bane of all remote sensing specialists' existence, is clouds. Like, we cannot see through clouds. They obscure what's underneath, and so for analysis, and actually a lot of computation, what we do is we build composites. So what we will do is we will take a stack of images of the same location, and we will take all the pixels that are not clouded, and then we will kind of smoosh them together. So we'll do something like take the median or average them. And you get these beautiful kind of cloud-free images, but you've thrown away all your temporal information. And that temporal information is crucial for things like vegetation, where phenology, how the spectral characteristics of a plant change over time, are very useful for identifying what type of vegetation that is, right? So can we dramatically improve the productivity of working with remote sensing data? And that was part of the motivation for the project that we started at the university called Tessera. Now, I'm not going to dive into too much depth on the actual model itself. There's an archive paper that gives you all the gory details. But at the high level, Tessera is an encoder model. So the way to intuitively think about it is if we have 2 different sets of observations of the same point on Earth, the representation, or as we call it, the embedding of that point should be the same. So if you have 2 different views of something, it should result in the same representation, so the same kind of semantic. And we built this model, and then we trained it on 800 billion non-cloudy pixel-wise time series. So we trained it on individual points on Earth, so 10-meter resolution. And what we get is we get 128-dimension embedding. So we get embedding or representation for every 10 meters on Earth. And what you can then do is you can then train models on top of that embedding. You can treat that embedding as a compressed representation of the last year's worth of observations of that point on Earth. And because we've actually done the work and spent the compute in learning those semantic features, you don't need to spend precious labels, supervised labels, like this is a tree, this is a field. You don't need to spend that when you're actually training your models on top of it. And what that means is it actually outperforms training on the raw data itself. So you can use, to get the same level of performance of training on the raw data, you can use 10 times fewer labels. And once you're in the region of 3 times fewer labels, you can actually outperform training on the raw data itself. And so you're not having to spend your precious labels, which are actually quite hard to get or sometimes even dangerous to get, in order to do that. The paper has about 6 different examples of where we've done this for different things, like canopy height. We've done it for crop detection, crop yield, all those kind of problems. So I do recommend having a look at the paper. Now, challenges. The hard part of this embeddings as data paradigm is actually making sure you have the embeddings. So this is our current progress. So where we have something in blue, that means that we have got the embedding there at 10-meter resolution for 2024. Where it's green, we've got the full 8 years. Each year of embeddings takes 20,000 GPU hours and 2 million CPU hours and requires 200 terabytes of online storage for that embedding. Because it turns out the world is surprisingly big at 10 meters. And so that's one of the biggest challenges we've got is actually doing this. And if you go to our GeoTessera repository, which I'll link in a second, you can actually see this updating over time as more embeddings are produced on the university's GPU clusters. Which brings us on to GeoTessera. So it's a Python library. We've got a camel version in the works, but it has a simple high-level API, and it lets you give it a bounding box and find embeddings within that bounding box. It downloads them, it caches them, and it also does the coordinate reference transforms, because it turns out actually uniquely identifying a point on Earth is very hard. And so there's multiple different ways you can do it, all of which have their own trade-offs, and you need to make sure that you transform between them, otherwise things go wrong. The library itself integrates with the existing ecosystem, so you can get NumPy arrays out, you can also get GeoTIFFs out, and it supports lazy iteration of embeddings, so that you can do a computation over a very large area, but with only a small fixed memory overhead, which is actually, given the size of the embeddings, is actually really useful. So now I'm going to do a demo, and the demo we're going to do is, the hard part is going to actually be seeing the screen here. Okay, so this is some code. We're going to go through this code in a second, but what I need to do is find, oh, there we go. Oh, that's the way to do it. Right, I'm going to leave this code running. Oh no, I've run it. Right, so this is the UK. And what we've done, what we're going to do is, our problem is going to be, can we find solar farms? So here is some solar farms that we have labeled by hand, somewhere in the kind of west of the UK. And if we zoom in on these pink points, you can see that there's solar farms. And we've also picked a random sample of points that are not solar farms. And that's our training set. We then have a test set, which we've spatially separated. Very important for geospatial tasks, because there's a lot of spatial autocorrelation. So we've created a separate test set. And then what we're going to do is we are going to step through this program. So what we do is we load up our bounding box. Bounding box is just the longitude and latitude that determines the area we want to do the computation on. We load our positive, negative for train and test. And then what we do, this is GeoTessera, GT. So we take our bounding box and you call fetch embeddings, and that gives you a generator which lets you iterate over the embeddings. We also need to know how many embeddings we have, just so we can give you a nice, pretty progress bar. And then what we do is we'll build up these matrices of embeddings. So for each of the labeled points where we have a longitude and latitude, we find the embedding at that point, and we build up these matrices, and we do it here. This is where we're actually iterating through the embeddings, and we're finding all the points. We're finding the nearest embedding for each of those. Then we can visualize those embeddings. So what I'm going to show you here. So how many people here are familiar with UMAP or TSNE? So these are algorithms for unsupervised dimensionality reduction. So we have 128 dimensions is the embedding. It's quite difficult to visualize 128 dimensions. So you want to reduce them down to 2 dimensions. So what we've done is we've reduced the embeddings down to 2 dimensions, and then we've colored them based on whether there's a solar farm or not, right? And you can see that those embeddings are incredibly rich, because actually they almost cluster immediately into 2 clusters that are totally separated. And on one side you've got the solar farm, and the other side you haven't. So if we were to then run this code, what we would see is we ran it, and what we did is we've gone through and we've rerun it a number of times with different numbers of labels. So with just 2 labels, so just one positive and one negative, we already hit 88% accuracy on classifying these things. If you've got 10 labels, so 5 of each, you can already get up to 98%, and it just keeps on climbing from there. And this is with a very, very simple pixel-wise logistic regression classifier, right? So this is probably the simplest classifier you can imagine. It's a single linear layer, and we are training pixel-wise. So just, there's no spatial information. If you were going to do this as a kind of production thing, you would almost certainly want to have some kind of convolutional neural network that takes into consideration some spatial information. So this is the output, and we'll zoom in here. So this is the test set. So it's not been seen in training, and you can see that these black areas here are the ones that the models end up. So white is no solar farm, black is solar farm. And you can see that even an incredibly simple linear model put on top of those embeddings is able to, sorry, it's a bit laggy, is able to actually identify where there is a solar farm. And so that's the quick demo. And we have less than a minute for questions.
Hello? It's working? Okay. Yeah, okay, so thanks. Very cool. I mean, I worked on this, so I also think it's cool. But I have a question. So this is basically compressing the information within the year of satellite imagery to a 128 dimension embedding. So that's very good for doing correlations and classifications like these. But if you think from the perspective of an ecologist, they want something like in DVI, they have theory for like why that correlates or is causal to something that they want to predict. How do we convince, or how do we make sure that this is something that people would actually want to use?
Well, we know it's something that people actually want to use because we've been doing workshops where we've taken ecologists who would otherwise not have done this because it would have taken years or longer of analysis of remote sensing data to do, and they've got results within kind of half an hour of labeling, thanks to actually to your system. So it's a bit of a plant question. In terms of interpretability, that's something where we have to borrow a lot of what's happening in the LLM space for interpretability. So we've got a project where we're then trying to do sparse encoders on top of this to look for features that we can then label and say these particular features indicate this property and that property. But from the embeddings themselves, they're just dense 128 dimensional representations. So they don't necessarily have anything interpretable about them until you do that work.
Right. One follow-up to that is about the economics of this. So it's obviously a very big challenge to get all the embeddings, and we do want to provide them so people could work on this without duplicating work of doing inference. But given that models are still evolving, and you would expect that there would be new models with better architecture, who would be paying for this? Like, we cannot reasonably regenerate everything across the world every time that there's a new model, right?
No, but in the grand scheme of things, while 20,000 hours is a lot of GPU time, it's actually relatively small compared with like how much GPU time you'd spend on, say, training even a small LLM, right? So for the productivity increase that we've seen from the users of this, even just this level is probably fine. Thank you.
Any other questions?
Tim.
So this is identifying a fairly regular structure
Yeah.
in solar farms. Can you apply this to sort of find more organic sort of structures in the landscape?
Yes. So the thing to point out here, this is pixel-wise, so it's looking at every single 10-meter pixel, right? So it's not even considering that, oh, I've got this pixel that's likely to be a solar thing, and actually it's in the middle of a playground, right? If you were to use, if you were to include the spatial structure, so with something like a convolutional neural network, you can identify those kinds of structures. And we've got work in that, and the paper actually has an example of one of those.
Okay, very cool.
Cool.
Let's thank Sally again, and now we're going to move on to bring Adi back on stage again because he's got a demo for us about what they're doing in India for the use of the spatial temporal catalogs, but this time augmented with data flow graphs in order to run pipelines of computation across a lot of the hydrology and other data sets we heard about earlier from him as well. So Adi, once you get set up, why don't you take it away?
Thanks. The broader initiative in which we're doing all this work is called the Core Stack, Commoning for Resilience and Equality. So just to give a high-level picture, basically we're trying to bring, to develop a good place-based understanding, right, at a very local level of any of these places so that we can think about what kind of ecological stresses it might be going through or what sort of actions can be taken. We are trying to bring, a lot of different data sets together. Some of these we are generating in our own lab, tracking land use, land cover over time, and hoping to use Tessera and other things for it, and similarly water stress and so on. On those, we then compute for different spatial units like villages or watersheds, micro watersheds, we compute a whole bunch of indicators. And that's why we're also trying to do more modeling, like the hydro GPU work that I talked about. And all of these, we're in the process of now, these are all currently running as isolated pipelines, but we're now trying to bring them together in the StackD method that I talked about. So while all of this is accessible openly and through APIs, we're also building a bunch of dashboards. And here the primary user is either NGOs or civil service organizations working in these areas, or community members, farmers, and so on. So I'll show a quick demo of some of these things. So for example, Know Your Landscape is meant more for like a large NGO to plan, right? What sort of works they should do in different parts of an area. Commons Connect is now an Android application, which is meant to be in the hands of somebody in the community, like a community volunteer or an NGO frontline worker, through which they can do micro planning, that what are good places for farm ponds or check dams and so on. And then we're doing a bunch of work around impact assessment and everything. And the outputs from these tools, we try that they can be plugged into different government schemes. These government schemes in India, they finance many of these natural resource management structures or different sort of incentives for farmers to move to natural farming and such things. I'll give a quick demo of Know Your Landscape to show what this looks like. We've automated pipelines to generate all of these data sets at equivalent of a sub-district level in India. And these are all, it takes us about a day to generate a lot of these data sets for any given area. So you can also look at a report. These blue boundaries are micro watershed boundaries, black boundaries are village boundaries. So you can do things like, you can look at a report of a micro watershed where the NGOs can understand what is the terrain like in the area. There's some pre-computed stats like how much area is under what kind of a terrain. And similarly, change analysis that over the last, since 2015, have trees changed to built up or has area come under from trees to cropping. Then another important parameter is cropping intensity, that in India, a lot of the agriculture is rain-fed, which means that there's, in many areas, there's less irrigation water available. So how many areas are able to plant just one crop in a year, which is during the rainfall season, or whether areas are able to do two crops or three crops and so on. So these sort of changes can be seen. Land use, land cover graphs. How is surface water availability similarly changing? So for example, this is a dam on one side, and we basically do seasonal water detection, right? So the dark blue is perennial water. The light blue is sort of water that stays during the rainfall and the post-rainfall season, and rest of it is just seasonal water. So these kind of things, when put together, they can help us understand which areas might be, right? So we also bring in, for example, drought analysis and so on, right? And how is groundwater behaving in the area. So all of these things put together for a given unit can help in terms of planning, right? That which areas are more drought prone, and also they have some kind of a surface water stress, they have some kind of a groundwater stress. And then we also pull in data of different villages, that what are the villages in this particular area. So there's also India has a policy in place for affirmative action for lower caste communities. So some of those stats we're able to see. And then there's a lot of government schemes that fund many of these activities. So which villages have had what kind of works is also here. Right, so this also, at this unit level, we then also allow people to play around, that they can start defining what we're calling patterns. That let's see areas which are mostly plain, right? So behind this, we have all these raster layers of which areas might be at the bottom of V-shaped valleys or U-shaped valleys. So there's an algorithm called the topological position index algorithm that we use to derive this map. And here we are basically just discretizing it in coarse categories, that which areas are plain or they have a mix of plain and slope. So there's some hilly areas over here. And then bringing in this climate data, that let's see which areas are also more drought prone, right? So now you know that these areas are more water stressed, right? And likewise, which areas also the surface water sort of dries up after the monsoons. Yeah, so these things can help you, right? Likewise for restoration, right? Reduction in tree cover and so on. So these can help NGOs or anyone working in these areas to figure out, right, that for areas following this kind of a pattern, what could be done. So some of the other interesting things, right, that this also allows is that you can start writing expressions of this sort, right? Or right, that in areas where the aquifer is of some type and the terrain is a mix of plain and slopes and so on, right? What might be things that you can do? So you can write logical expressions, but what we are also trying is that because local organizations working in these areas, they really understand what works. So can we use this as a way to codify their local ecological knowledge and traditional knowledge? How much more time do I have? Okay, then I skip this demo of the application. Here, it's now in the hands of somebody from the community. And what this allows people to do is, there's some decision support tools built into it, that is this area good for a farm pond or a check dam and so on. And then people can fill a form that for that particular structure, what are the dimensions and so on that they want to plan. And they can generate a village development report or a village development plan, which can then be submitted to the government officials. So this is really helping, because now you're able to get more data-driven, bottom-up planning happening. And it's also very important for empowerment, because often what happens is that communities do want many of these structures, but they're not able to justify to senior government officials about why they want it, and right, there's a lot of corruption and so on. So here we're kind of giving credence to what the community is saying, plus we're constructing a digital trail which brings transparency. So now it becomes much harder for anyone to sort of deny these things. So let me then quickly show this demo of StackD, which I talked about earlier. So this is like a toy example. Right, that let's say you have some of these layers, you want to run a LULC on it, you want to run a terrain classifier on it, and then you want to sort of know that areas which are mostly plain, what sort of, are they forested or are they cropped, right? So this is this LULC cross terrain kind of a vectorization. Here, we express this in the StackD format, and I hope
the user specifies the entire workflow in terms of YAML config files. There is dag.yaml that defines the entire workflow. Then there is algorithm repo that defines the actual instances, their assets, the execution modes such as Docker or API based, and then the other details required for this execution modes. Then there is also the dataset repo containing the initial datasets required and the DAG generator script that takes all these YAML files and creates our DAG that is fed to the Airflow execution engine. Then we go on to execute the Airflow in backend, and we can see our DAG and the Airflow dashboard containing all the dataset nodes and the dependencies that we defined in the DAG. Then we trigger this DAG based on certain trigger parameters, and you can see that this DAG has been triggered for the given year and the given region, and all the nodes are successfully executing. The determine execution path is for the selective recomputations that we have defined in the stackd format. As you can see that Airflow has triggered both of the algorithms in two separate Docker containers, and then the scripts run inside these Docker containers and they trigger tasks on Google Earth Engine that create assets in turn that will be used by the next set of algorithms in the pipeline that has been defined in the YAML. So you can see that parallel pipelines can execute simultaneously the terrain vector and LULC. We can also see the logs of the execution of the script on Docker container for any debugging or error resolution purposes. The triggering of the algo leads to a blocking call, and Airflow will only move forward once the asset IDs of the created asset on Google Earth Engine or any other platform is returned by the algorithm that has been triggered. As you can see, more and more algorithms are triggered. You can also do lineage visualization by providing the dataset name and the version, and the backend database fetches the lineage details for you so that you can visualize the lineage of any particular dataset and its version correctly using our Airflow dashboard. Finally, all the nodes have successfully executed and created their assets on Google Earth Engine by triggering with the help of Airflow. As you can see on Google Earth Engine, all the assets have been successfully created for each of the algo, raster, vectors, everything has been created. We can check these assets also. As you can see, this is the asset for Dumka Masalia LULC map. This is the asset for vectorization, and it shows all the features and properties as well.
So yeah, where we are currently, there's all these data sets, and right now it's of course us doing it. We're trying to move everything to the stackd format so that it's not like individual pipelines, but the whole DAG can be triggered for given locations. So here, a lot of the computation actually happens on Earth Engine, or some of it happens locally on GPU workstations. And all of these datasets are then published onto GeoServer, from where some of the front-end tools that I was showing, Know Your Landscape and so on, they visualize. But potentially, the whole idea behind going forward with the stackd approach was that these DAG specifications can then be shared with other people. So potentially you can have anyone else setting up local instances and writing their own DAGs in YAML and executing them. And then thinking about new use cases, right? Not just the ones that we've done over here, but they can think of, right, maybe restoration or grassland restoration and so on are more important in some areas. So that can move forward, yeah? So I'll stop here.
Writing DAGs in YAML is one of my great regrets from working on Docker Compose, but it's good to see it being used for good purposes here. Does anyone now? Adi's already been on stage and has asked questions. So if no one's got any burning questions, we can discuss the tools and stuff at the evening session. Dominic, go right ahead.
So what about when they're not a DAG? What about when you have feedback cycles, which often does happen for certain kinds of models?
Yeah, I mean, we've not thought that much about it, but especially when some of this retraining is meant to happen and stop at a particular point, so we do need to think about it. Yeah, for sure.
Let's thank Adi again. So the next lightning talk has been 30 years in the making. So the Titanic Robin Milner began the line of work that has now been taken up by Ryan here. No pressure, and they will discuss spatial programming for environmental monitoring. Take it away, Ryan.
Okay, so I'm going to talk about spatial programming for environmental monitoring today. So, there are a vast amount of environmental sensors out there in the world. They span different regions, organizations, jurisdictions. There's carbon flux towers across the Amazon basin. There's marine salinity monitors in buoys drifting in the Pacific. There's acoustic monitoring of coral reefs. And to give you an idea of the scale of this kind of thing, this is a map of acoustic monitoring projects out there. These are not sensors, these are projects. So each one will have hundreds of sensors themselves. So what we're thinking is, how can we support programming with these kinds of spatial devices? How can we express things like allowing ecologists to access data via link local networking, but not poachers? How can we broadcast to a spatial domain if there's an event like a flooding and we want to notify people? How can we perform an action in real time based on triggers? So if an acoustic monitor detects chainsaw, can we wake up a co-located camera trap to detect that? And how can we do this all between organizations and across different country boundaries? Today's architectures typically ship data to central servers, manually replicate that between organizations, and require custom APIs for each collaboration. It's very static, but we want to push this into the sort of real time on the edge. Enter bar graphs. So bar graphs are a formalism from the 2 decades old, and they express containment on the left and connectivity on the right. So this is, on the left, this is a forest of spatial containment. So an agent can be inside a building can be inside a city can be inside a country, and so on. And a link can be a communication between two agents. This is very general formalism. It was kind of created to, in part, encode a number of other process calculi, like the pi calculus and Petri nets and so on. But we're focused on modeling the real world with it, which was kind of the original intent. So here is an example of an urban network encoded in a bar graph. On the left, you see the physical layer, which are sensors. And we can express more like social and human representations here as well, virtual encodings. So we have the data layer on the right, which is where we're gathering data, and we have an application layer on the very right, which processes this data. Thanks to Roy here, we have code to derive bar graphs programmatically from OpenStreetMap data. This is a lot of nodes, but we've summarized it here in a hierarchy, and you can see we can partition the world according to these logical boundaries. So I opened this talk with spatial programming as the example, and so far I've just talked about this strange formalism from 20 years ago. But we can actually program space with this formalism. And an intrinsic part of the bar graph specification is reaction rules. So we can describe transformations of this system based on pattern matching. And this differs from existing process calculi in that the user can specify how to program these systems, right? So here's a very simple example. On the left, we have an agent in a room, and on the right, we have the agent moving out of the room, okay? And these open links show you that it can compose with other graphs and other reaction rules. And on the bottom here is the textual representation of this reaction rule, although the graphical representation is mathematically valid too, which is a neat property. This is an example of applying this reaction rule to a graph. On the left, we have an agent and another agent with a contact in a room, and then on the right, the agent leaves the room. And we can express policy using these reaction rules. So here we're saying if two agents are in the same room, we can create a contact between them. And you can imagine a very similar thing for creating a communication link to a node that you're co-located with. We could also add social boundaries here, like you can only do that if you're a member of a certain organization. But these bar graphs have been relegated to primarily a mathematical domain. There's been a heavy focus on the formal semantics, applications being in encoding other process calculi, with tooling targeting formal verification and like little uses in real-world systems. So we're trying to do that, to fix that, to use them in the real world. And so we tried programming with these things, and the first thing we ran into is we want to encode state in these nodes. And that is not something that's easy to do in the bar graph formalism. It is expressive enough to do so, but you need to jump through all these hoops to represent it in the formalism. So we created a runtime where we support properties of nodes. So you can do things like express the battery life or the value of a certain sensor, or what else? The role of a person in an organization. And this allows us to be a little more expressive with these reaction rules. And we also support side effects as the result of reaction rule applications. So we can do things like when we detect a chainsaw sound as a property of a node, we can perform a side effect, which is to wake up a co-located camera trap, for example. And I've talked about how to theorize and reason about these models, but I've actually not talked about how you can use them in the real world. And to do so, they communicate over a network. And in the real world, there's very complicated networking scenarios for these things. They're often on mesh networks. They're often not globally addressable. They're often not first-class nodes in the network. So what we think is a good way to network these devices is to identify them by their location. So using bar graphs, we actually already have a unique name for them, which is their location in the place graph, right? We might have sensor A in forest stand A in the Amazon in Brazil. And this looks a bit like a DNS name, right? If we have domain names for these devices, they're first-class entities in the network, and that means we can do things like provision TLS certificates for them with the ACME protocol. I know this isn't a networking conference, but we do need to program them in a distributed way. Hardware replacement is transparent, with new devices subsuming the identity of their predecessor, and we can resolve them to link local addresses when we're co-located with them. And when we're not, we can resolve to global addresses. So for example, Bluetooth, LoRa, WAN, or even audio. And I talked about, in the introduction, I talked about multicasting to a spatial domain, and we can actually express this in bar graph reaction rules as well. On the left here, we have a message which we want to propagate down a boundary, and on the right here, we have propagated that message into the boundary. And we can support spatial multicasting using this reaction rule applied iteratively. So far, we've only talked about the human representation in a hierarchy of these devices, but obviously in the real world, they have a coordinate, right? So we were thinking, how can we query what nodes are within 5 kilometers of me, for example? The bar graph formalism has a very convoluted way of encoding this, but we want something performant and real, so we've got a OCaml R-tree implementation that, thanks to Patrick, that we can use to efficiently query devices in the real world. And this can scale to the globe. So our runtime for this is called Bifrost. It's an OCaml library with support for processing bigraphs. It can be integrated with this spatial indexing, the hierarchical name location-based DNS, and the OpenStreetMap data. It scales to 10,000 plus nodes with less than a millisecond rule application on constrained hardware. And we can use the composition of bigraphs to delegate control to a local region. So we don't want to rely on the network access in a scenario where we might have intermittent connectivity. So we can delegate a portion of the bigraph to a node and have it operate independently and only reconcile that when it regains network connectivity.
what these abstractions bring us is spatial access control, so we can make that a first-class dimension of our programming. Location-driven rules, such as the example of triggering a camera trap when we detect a certain noise. And we can use this mergeability property of bar graphs to support delegated operation. And we can do this all with low latency, because we can delegate to a subdomain. Privacy, because we don't need to share that data unless we have an explicit rule to do so. And robustness during network partitions. We think we need space as a first-class concept in programming in order to enable all these applications, paving the way for scalable, composable, and responsive monitoring networks. So future work is looking at more granular non-built environment representations, because at the moment the OpenStreetMap data is pretty urban specific. And we do think there are use cases in the urban environment, but I was speaking to Adi about forestry stands and how that might be represented in this system, which was quite interesting. Bar graphs are a pretty low-level way of encoding a lot of this logic, and a sort of open question in the field is how we can write a higher-level language to express spatial access control policies. And finally, we want to do some real-world deployments of this thing. Any questions?
Thank you, Ryan. Over to you, Michael.
So I mean, I totally buy that, you know, the spatial concept should be, you know, represented in first class in these kinds of applications. I'm going to ask you a reframed version of the same question I asked earlier today, which is, we've got this formalism, there are people with some needs. How do we know whether the formalism matches the needs, or whether actually there may be a bunch of needs that we need a different formalism for? Do we know what the requirements are here?
So I think it comes back to this: how do we do this between organizations and across administrative boundaries? There isn't really a standard framework for expressing these kinds of policies. Maybe we don't need one. Maybe it's enough the state of the world as it is.
I mean, even embedded in this, like what is this? Like, have you gone and talked to scientists and gotten a catalog of, like, here are all the things, here are the applications we would like to build that involve sensors and geography, or data and geography?
No, this is something that is certainly worth doing, though. Yeah.
Do you want to perhaps briefly describe the conversation with Adi? That might give a bit of context.
Yeah.
And a user to connect the dots.
So I was speaking to Adi this morning about this very thing, and correct me if I'm wrong, but it seems like it's very long-term and static.
What is a forestry stand? Give the audience a bit of context.
Sure. A forestry stand is a particular region of a forest, and there's various monitoring that the core stack is doing on water levels and rainfall and other things, as I understand. And this tends to be taken in the aggregate over the long term, but there's little like real-time, low latency programming over this data, right? These scenarios that we talked about at the start are not supported, if I'm right. Yeah. Mm-hmm.
Have a full survey of scientists everywhere, but at least we have one data point coming out of PROPL. Let's thank Ryan for the demo and the co-authors here as well. Oh, we have one question. Sorry, did we miss a question? Who was it? Oh, sorry. Go right ahead and go right ahead and just jump up to the mic.
No worries. If I can remember it now. So so you gave the example of organisations and sort of jurisdictions, but the point you made about the kind of spatial containment seemed to suggest that these structures are always trees, whereas organisations often are kind of cross-cutting, and you can be a member of multiple jurisdictions and things like that. Is there a kind of generalisation of bar graphs where you might want to represent DAG-like structures rather than trees?
Bar graphs with sharing, yeah. There is some issues with composability of these things, but the formalism does exist, yes. No worries.
Very basic question. Maybe you said it and I missed it. Why bar graphs? I mean, like, I just want to know, like, if probably PyCalculus or variant other calculus, ambient calculus, or any other actor-based formalisms. Probably in ambient calculus, that if you want to do some sort of term rewriting, or maybe it's easier with that formalism. I'm just wondering why backgraphs over other formalisms that you have.
Expressive, but it doesn't support these user-defined rules, for example. You need to go out of your way to encode the logic in the ambient calculus.
Okay, but even if you have like two different spaces, which is your logical space and physical space here, like how do you, like if you want to do some sort of bisimulation checking between both of them, how does that look in bigraphs? What, like any verification angle in bigraphs? Do you have any opinions on that or any comments on that?
Should we have a talk after the? Yeah. Okay. Thanks for the question.
Round of applause because I missed the people asking. Thank you. Run bisimulations using bigraphs in 2007. So probably something to start from. And then Luca Cardelli had lots of opinions about ambient calculus as well. Right. And Michael, do you just want to do a quick sound test first?
Yep. Can you hear me?
We can hear you perfectly. Half of your face is cut off, but that's okay. We've got the good half. Go right ahead.
Excellent. Good afternoon. I'm going to hear myself, so I'm going to have to move speakers down. You'll have to ask questions at the end. So I'm going to run through, give a quick demo of Jaeger-Sheffer, which touches on a couple of things that we've already had today. So Jaeger-Sheffer is a declarative geospatial library for Python. And it's kind of got two main aims. The first one is to get rid of all bookkeeping associated with geospatial work, like aligning layers, polygons versus rasters, and so forth. And also to get rid of the bookkeeping associated with computers. The geospatial layers being very big, and kind of how do we deal with memory and parallelism and stuff like that. For this audience, I think it's a Python library, so it's probably not the most exciting thing you're going to hear about today. But what I hope is that this inspires kind of further work in this direction. I think this is, I'm kind of pleased with what we've achieved, but we are limited by what we can do building upon the Python base. So hopefully there's ideas here that can kind of run forward in a more rich fashion somewhere. The one thing Jaeger-Sheffer does have going for it is it's been used significantly. So for the last 3 years, I've built kind of 3 large-scale ecology pipelines based upon it. So this one here is the life pipeline. So this map shows you the increased probability of species extinction if you convert a pixel of land to a farm. It's a lot of work, 3 years, petabytes of data to tell you not to put a farm in the Amazon, please. But so it's kind of, this is a result of running hundreds of thousands of species through Jaeger-Sheffer. So with that in mind, we do some demos here. Kind of first thing is it's available on pip. You can just pip install it, and then you import it, and you're ready to go. So using Sadiq's example earlier of cloud removal, which was unplanned but very helpful, I'm going to use cloud removal as kind of like our initial example. So here we're going to load 2 satellite rasters. And not much happened there because Jaeger-Sheffer will lazily evaluate things and it only actually reads data when you're trying to aggregate it or actually raster the final result. these two layers there, let's have a quick look at them. So here we have a visible layer that's trying to show vegetation, and as we explained already, there's cloud all over it. And then the satellite layer also comes with the second raster, which is the scene classification layer, where every pixel is enumerated to say what is it that's there. So we can see we've got shadows, vegetation, water, and cloud. And so to remove the cloud, this is where my demo is wrong. This should not be like this. So to kind of remove the cloud, we want to say take the scene classification layer where it is these specific values. Those are the bad pixels, and then we're going to use like a NumPy style where operation. So YogaSheffe, where it can't use Python primitives, models itself on existing data science libraries. So where is bad is true, we'll just have a null value, or we can read the vegetation layer and we'll save it out. And that then gives us a map with all of the clouds cut out of it. And then you can take several of those, as Sadiq was saying, and smoosh them together to make a cloudless layer. This is hopefully kind of keeping the code like the method. The syntax is very Python-like. You never had to worry about pixels. You never had to worry about aligning the raster layers. So from that point of view, it's hopefully better for the vernacular developer, as Patrick was describing earlier. And it does a lot of similar things to Google Earth Engine, but Google Earth Engine's APIs are very programmer kind of focused, I think. So hopefully this is somewhat cleaner. But it is inefficient. So for things that need to be improved and worked on, right, this expression, although it's made the scene classification layer look like a Python primitive, that is actually a big raster which we have to load in chunks of, and we're evaluating it 4 times, which is terrible. So kind of what we should be doing is kind of we could write it more efficiently. I can get rid of this, and I can describe is bad as the kind of scene cloud layer. We do is it in one of these classes? Let's just pick one for now. And then if we rerun that, we'll get some of the cloud gone because I didn't put all the classes in. But this is, again, very programmer focused. What would be nice is if YogaSheffe could just detect that we could do this more efficiently. So that's kind of one area for improvement. So next demo. So the next example is kind of building the area of habitat for a species, which is what that map I showed you earlier was built on. It was like 120,000 area of habitat calculations go into that map. So this is a standard method that's used for many biodiversity metrics. And we're going to look at how do we calculate the area of habitat for this azure-breasted pitta, which lives in the Philippines. So you start with this IUCN red list data. So we got the range, which is a polygon saying roughly where the animal is. And then we're going to combine that with high resolution satellite data to further refine to where we think the bird can be found. So, so running through this, we load our data layers again. We just load them all, including the polygon. Like the polygon isn't treated specially. We just, it needs a slightly different function name, but again, there was no special processing for it. Here's our three layers for the area of habitat calculation. The habitat map is just an integer enumeration where pixel, it'll be a number that says this is temperate forest, or it'll be deciduous forest, or it'll be ocean, or what have you. And we have a high resolution elevation map, and we have the polygon of where we think the animal is. I'm also going to pull from the GeoJSON just a couple of, this is the elevation preferences for the species, and then the habitat classes. And then we can just work through the AOH method, right? It's give me the filtered habitat map, which is in, just gives me the pixels with those habitat codes. That's evaluated lazily. I can query it for the metadata, so I can find out its range and its data type. But it's not until I actually force it to be rested that Yoga Sheffi does any work. So this allows you to kind of build up more complicated expressions as you go, but only have it do the actual work that's needed at the end, which I'll kind of exemplify in the next quick demo. So again, similar for filtering for elevation. Again, we go for that, and then we combine those rasters together to give us a final AOH. It's not a huge visual exciting demo here, but it's hopefully you can see that the code that I'm writing and executing to evaluate this is free of the kind of clutter of the actual bookkeeping that is normally associated with this work if you're using something like GDAL. So yeah, then finally we get our area habitat. This is where in the Philippines we would likely find that bird. And we could multiply it by, here we have another raster where every pixel is just the square meterage of that pixel. And so we could actually just do an aggregation to get the total. But that is a kind of very simple view of what was actually done in that experiment to make that map, because there we're working with global data sets. I'm just going to set this on running. So here we're loading the full global habitat map, which is 400,000 pixels by 200,000 pixels, and int 16. So each layer is 150 gigabytes. So that's 300 gigabytes off the bat to calculate the area of habitat for a species. My laptop does not have that much memory. And even on servers where we do, we want to get parallelism from processing many species at once. So memory is a huge bottleneck for this kind of calculation. But Yoga Sheffi can do a bunch of tricks, right? So one is it can chunk the data up and process them in chunks at time, so we don't bother the ecologist with having to read in a bit, do some work, save that bit, and that kind of typical loop. But also because we're lazily evaluating, we can see that we know that the range for species is of a limited area, and we know that we're doing a multiply here, and so anything outside of the range is 0. So we don't need to calculate the rest of the globe. We'll just 0 all that. And so Yoga Sheffi can also, because you're only doing the work at the end, kind of limit computation that way. So we get some parallelism and some kind of memory benefits from this, but we are constrained by what you can do in Python. It is still hugely inefficient compared to if I was writing this in a more parallelism-friendly language. I can't share the global rasters for habitat between all of my sub-processes, for instance. So yeah, even though this takes a long time on my laptop, it's all demos ended with a memory error. But yeah, hopefully that gives you a flavor of what Yoga Sheffi can do. And I hope that you can see ways in which we can take this forward if it wasn't constrained by Python's limitations. Cool, that's it for me.
Applause from the room in case you can hear it.
Thank you.
Now, do we have any questions for Michael? Michael, can you hear us?
Yes, I can.
Excellent. While we wait for questions, what language would you have written it in if not Python?
The main thing was where I tend to better share memory. Because of the way Python multiprocessing works, it's just very impractical to take those big global layers and spread them out, because you have all these species where you want the same data, but you're having to load it multiple times. So that's kind of anything that's got good concurrency primitive and good kind of memory sharing primitive. Oh, sorry, I meant a camel. Sorry.
Staying up so late in Cambridge, and we look forward to seeing the Ocampo version of Yoga Sheffi.
Cheers.
Thank you. And now we're going to shift for something quite different. We're going to just have a panel.
Okay. Okay, I'm going to try again. So, I think that's, I'm just speaking to Dom. I think that's, okay. I think we're going on to the next session. No problem. Well, I can do it now if you like.
No, I think I'll message Jay. Let's just move on to this one.
Okay. Well,
Thank you for coming, everyone. My name is Andres. I come from Colombia. I'm advised by Anil and Ronita in Cambridge. I'm going to talk to you about how to map urban forests. As a non-technical expert and more from the environmental background, I'll show you how I use all these programming tools to map trees in England. So why trees? This picture was taken like 2 days ago when I arrived. And I think like pretty much everyone agrees that trees are super important because they provide a lot of ecosystem services. They're places for social cohesion, not only like from the nature perspective. They provide air pollution reduction, temperature regulation, and are the staple nature-based solution for cities, which here in Singapore is a prime example. Singapore originally was covered in forest, and 95% of it was removed to build a city. So like 30 years ago, the government here said we're going to create a city in a garden, which they have successfully built, even though like well, it's very urbanized. There's a lot of trees. Sadly, I'm not going to talk about Singapore. I'm going to talk about England. But first, I'm going to introduce a conceptual framework that was created by the urban forestry community, which is called the 330-300. It essentially says that you should be able to see 3 trees from wherever you are in a city. Every neighborhood you have 30% canopy cover, and you should at least be 300 meters away from the closest public park. So taking this conceptual framework, many cities around the world in the last 4 years have started to like quantify or sort of measure if they're actually approaching this goal. But I took it a step further and I did all of this at the national level because every city has its own different approaches. So what I'm proposing is a framework like a standard framework that can be transferred to different cities around the world. For that, well, for those of you who have played around with geospatial data, and as Sadik and Michael have said, like there's a lot of different nuances with spatial data, the coordinate reference systems. We have vector data, raster data, graph data, which is a key component in this project. And then there's the scale. So in this particular project, I'm working with like all the buildings in England, which accounts for 29 million buildings, of which 24 are residential buildings, 3 million roads, and 16,000 public parks. And then I segmented almost 200 million trees, or 190 million trees in all of England. And how do I measure this at a granular level, at the building level in all of England? So this is what I'm going to show you. This is the programming part aspect of the talk. So as a non-expert in like computer science or programming languages, I'm mostly familiar with R and Python. And this is the full stack of tools that I've been using, mostly like LiDAR from R for tree segmentation, and then like a bunch of different libraries in Python for handling spatial data, parallelization and partitioning of spatial data, like Sedona, GeoPandas, Xarray for raster-based datasets. And this is what it looks like. This is the tool. This is the tool that I created for the tree segmentation part, where we can see all the trees in England. This is for Cambridge, and we can the output of the whole process is a point for each tree, where you can see the top of the crown and the height and the area of the crown. So you can see like the different kinds of trees. Unfortunately, not species, just like dimensionality of the trees. And how did I do this? Essentially, what's happening is I'm taking LiDAR-based rasters that are processing in R using Del Ponte and Coombs algorithm and a local maximum filter to get like the top of the crown, and then model the rest of the trees according to that. And that's where I get the 190 million trees, which kind of looks like this for a park in London. So what you're seeing here is all the buildings in this particular area, which ones are actually close to having at least 3 visible trees. All the green spots are trees. and the red buildings, well, 0 all the way to 9, within 25 meters. Then we have the canopy cover. This is a more standard geospatial like modeling, where you do zonal statistics using the same data set. I created, and using neighborhood data, you can model the canopy cover per neighborhood in England. And then the 300, the distance to the park, which is probably my favorite aspect of how I built all of this, because it uses the graph of roads. So the whole road network is used to create Dijkstra, or to calculate Dijkstra distance between the nodes that are closer to each building and to each park, to get where is the closest park to each building in Britain. And this is what it looks like. So I didn't mention this is in London, in Tottenham, and this is what it looks like. How long it takes in actual distance to walk in the built infrastructure to get to a park from your house or from your workplace. And so this is the power of all these geospatial tools. But in addition to this, I took it a step further to use satellite-based imagery to like get more traditional spectral indices, namely water, vegetation, buildup, that looks something like this for the same area. So we can take like vector-based data sets like the 330-300 with more traditionally traditional data from the remote sensing domain. And this is the end product. So we can map all of these variables for all parts of England and see where nature is more needed in urban areas. And finally, well, this is the first national assessment of the 330-200 rule, plus additional variables to complement other aspects of nature. This is a reproducible framework where we take like vector-based, raster-based datasets that are available in other countries as well. And it also uses open source data and libraries, unlike many different companies that produce similar datasets but with proprietary data. And this is an evidence-based like quantification of greening policies. Then the future step is obviously to transfer this to other areas or regions of interest in the world. And yeah, if you want to play around with either of the demos that I just showed, the first one is the tree segmentation, where you can see all the trees. The second one is the map with the zonal statistics of the different metrics, or you can see the code and contact me. Or you can see the poster later today and ask me more questions.
Thank you. How many trees did everyone think were in London? Go ahead. If you have any questions, go right up to the mic.
Sure. I have two quick questions. The Dijkstra diagram,
yep.
I didn't quite understand. It looked like some of the houses that were very close to the park were very far in the color.
This one?
Yeah.
So yeah, like this one is actually modeling the distance between the access point to the park and the closest to the building.
Okay.
So it's not like like to any point of the like the park geometry is the access point.
Okay.
So it's a true like measure of walking to where you get to the park.
Right.
Yeah.
Okay, that makes sense.
Yeah.
The second question was: is there any relation between these metrics and deprivation in a certain area?
Yeah, there in the paper that it's in a preprint. I cannot share the QR code for now. There are relationships between deprivation and nature accessibility in England. There's this thing called index of multiple deprivation that measures different levels of like socioeconomical conditions, like health, crime, income, and there's definitely a correlation between number of trees and level of deprivation. So like poorer areas tend to have less trees, but contrary to what you would believe, poorer areas have, or on average, live closer to parks. So that's something interesting that we found,
Mhm.
which is like, is not what you think. Like, you would think like richer areas have like park like at 10 meters, but it's not the case. It might be because they have gardens. So like many houses have their own like proprietary green spaces, which were not accounted for in this particular analysis.
Okay.
Yeah.
Thank you. Do we have any other questions? No? In a weird coincidence, I used to live there in 1997, and you can actually jump across a fence to get into the park. So
oh, really?
You don't have to go all the way through, but the police do keep an eye out for you. So.
Yeah.
Let's thank others again.
Thank you.
web-based interfaces and large kind of data management things. And it's clear that if you put a mesh together, that we could come up with some really interesting technologies where we could make them better. The question really is, can we make them 5 times better? Can we build transformative experiences that will change the way that we operate in order to meet the goals that we have here as well? And of course, the third thing that's happening here, not just technological improvements in programming languages and in data capturing and so on, is that LLM and more generally machine learning technology is accelerating faster than almost anything I've ever seen in my career. So our challenge here is to try to figure out how we can put these pieces together and design for the interception point. So what will happen in a year, or 2 years, or 3 years by the time all of these technologies mix together? So we shouldn't be designing for the past, and we should be looking forward to the future as well. But then the awkward thing here is that we're working all over the world, and often in the majority world as well, where it's just quite difficult to get to. I spent my summer in Botswana, in the middle of nowhere. It was more travel time to get there than actual time spent there, because you're just really, really far away from things. And equally, following Adi's blog and so on in the core stack, a lot of time spent in remote villages and so on, where it's just difficult to get to. And we've seen just from the remote experiences of this conference how awkward it can be to try to build genuine collaborations when you're far away from each other. It's just a lower bandwidth, lower quality experience to try to kind of mesh teams together as well. So I think our challenge for PROPL in the future is a social one. The question is, how do we get disparate communities together, physically together, in order to have working spaces where we can really bash out solutions that solve immediate problems, but can network together in order to build bigger effects so we can start reusing things together. And we've got a few initiatives going on in this space. So there is the equivalent of Dagstall seminars and Shonans. One of them has just started up in India, and we put an application in for something called InDCS, which is aiming to host similar working groups for weeks or 2 together. So if that gets accepted, many of you can expect to get invitations. If you'd like an invitation, you get a free pass for coming to PROPL. Just get in touch with any of us, and we'll try to make that happen. But also, try to create communities locally as well. So one of the great things about Cambridge is we have something called the Cambridge Conservation Initiative, which is the university gave 10 NGOs a building. And this building houses BirdLife International, Traffic, the IUCN, and lots of people work together. The NGOs are there because they get free rent, more or less. And then the university provides free coffee and free housing. And we have amazing corridor conversations where things just happen because we're co-located. And there's a lot of movement happening towards this in other places. So there's similar initiatives here in Singapore. Stanford set one up in the Door School for Climate Change. And we need more of these kind of physical clusters of people working together. And then I'm hopeful that we can actually create a mesh of federated activity where we can occasionally go and travel to each other's places, but really you have the high bandwidth ability to work together and try to cross domains and really kind of bash out a code that can be reused by people but isn't immediately in the critical path. So that's my strongest encouragement, I think, is to try to set up these clusters. Tony?
I will just also jump in there because one thing I'd encourage you to do is, if you're at a university, find other people in the university who are writing code, who are programming for the planet already. You know, the earth scientists and the conservationists and things like that, and just grab a coffee with them and have a chat with them, because I can guarantee you they'll say, "Oh, I'm kind of stuck on this. Oh, you're a programmer, are you? I'm stuck on this thing. Could you look at my code?" And you could help them out.
Couldn't agree more. And as we've heard from Michael several times, getting the requirements and spending the time just to hear what they have to say makes a big difference, because often we found unexpected results from just listening to the practitioners and finding out what they actually want, which unfortunately is not rewriting everything on a camel, but that can be a side effect of solving their actual real problems that they've come up with. So I'm going to close PROPL on that note, saying that it means a lot to us that you've all come here in the middle of a really exciting programming conference. It means a lot as well to see the diversity of talks and the diversity of interest and action in putting things together. And thank you all for being so honest about the shortcomings and some of the places where we need to improve these things, because that really gives us all a call to action to figure out where to go next. So we have a Zulip where you can log in, eeg.zulipchat.com. Feel free to continue the conversation there. We're going to have a poster session in the main conference where we have a few posters, but really it's a place for us to congregate and continue some of the conversations we've started here today. So I'll be around by the posters all evening. I don't think I'll be eating too much food. And also many of us will be here for the rest of the week as well. So let's keep the conversations going. Let's use some of the Zulips and other social media mechanisms to talk to each other. And if any of the organizing committee can help to build some of these spaces and fabrics, we're always happy to do so. Cambridge, in particular, is always happy to be a home for any improbable plan that you'd like to come up with, just to see if we can have a go at doing this. And Adi similarly, and Casey in IIT Delhi and Madras are also very welcoming and hospitable and amazing cooks to actually put some of these pieces together. So thank you all, from Dominic, from me, and from Casey, and from to all the speakers and all the attendees for making this such a wonderful and constructive PROPL. We'll see you again next year. Thank you.